The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, on Tuesday we talked about sex, so today we're going to talk about marriage. Now, in terms of graph theory, marriage is expressed as a matching problem. And today we're going to talk about a matching algorithm that is used in all sorts of applications. It's used by online dating agencies to match compatible people together. It's used for assignment problems, for example, matching interns to hospitals on match day. It's used for resource allocation problems, for example, load balancing traffic on the internet. And we'll talk about the applications at the end of class. In its simplest form of a matching problem, you have a graph where the edges represent compatibility. Two nodes can be paired together or married. And the goal is to create the maximum number of compatible pairs. So let's define a matching. Given a graph G with nodes V and edges E, a matching you can think of it as a collection of edges or a subgraph of G where every node has degree 1. So everybody can be married just to one person. So let's draw an example. Let me not put that edge in. All right, let's label these nodes x1, x2, x3, x4, x5, x6, x7, and x8. Now, x1, x6 and x2, x5 is a matching. So x1, x6 and x2, x5 is a matching with two edges, so we say it has size 2. All right, so I can pair these guys up and pair these guys up. Is there any bigger matching in this graph? So I found one with two marriages, here and here, two edges. Yeah? x1, x7, x2, x6. Good. All right, that's a matching of size 3. So I got 3 couples together. Good. Can I make a bigger matching? One with size 4. 4 marriages here. No. All right, why not? Can anybody give me a reason why it can't be done? Yeah?
X8 and X7 both have to be matched with someone.
Yeah, so if, yeah?
So you can only be paired with X1, but X1 can't be paired with both.
Good. If I were to have a matching with 4 edges, well, there's only 8 nodes. So I'd have to have all 8 nodes involved in the matching. And that means X7 and X8 would have to be in the matching, but they can only be paired with X1. And so it's not possible to do that. All right, so there is no matching of size 4 in this graph. 3 is the best I can do. Now, when you get every node in a matching, then it's called a perfect matching. And so in this case, it doesn't exist, but sometimes it does. So a matching is perfect if it has size half the number of nodes. In other words, if the number of edges is v over 2, then every node is in the matching. All right, so that one doesn't have a perfect matching. What about this graph? So I got B1, B2, B3, B4, G1, G2, G3, G4, and I'll put in the compatibility edges here. Okay. Does that graph have a perfect matching? Can you pair up every boy with a girl here so that everybody's compatible with their mate and you have just one spouse? Can you do that? Yeah? All right. Who do I start pairing up? 1, 1. B2, G3. B3, G2. There we go. All right, so there is a perfect matching in this graph. Very good. Now, in some cases, some pairings are more desirable than others. And this can be represented with a weight. And so you might have a weighted graph where every edge has a weight on it. For example, we might weight B1, G2 with 5, and B1, G1 gets a 10. And usually when you see weighted graphs in the matching context, a lower weight means it's more desirable. So that B1 and G2 would get along better than B1 and G1. And then the goal is to find a matching with minimum weight. Now, the weight of a matching call it M, is the sum of the weights on the edges of M. Now, usually when you're looking at weighted matchings, you require yourself to have a perfect matching so that everybody gets paired up. And often in that case, you'll see all the edges present, some of them with very big weights, maybe even infinity, if they just can't be put together. Because otherwise, you just say, don't match anybody together, and you have weight 0. So when you look at minimum weight matchings, you're looking for the perfect matching with minimum weight. So we say a min weight matching for a graph G is a perfect matching for G with the minimum weight over all perfect matchings. Let's try an example. Say I've got this graph, and call this node Brad. Here's Billy Bob. Here's Jennifer. And then Angelina. And the weights are as follows. I put a 10 here, a 10 down here, a 5 here, because Brad really likes Angelina, and vice versa, and a 16 between Jennifer and Billy Bob. What is the weight of the min-weight matching in that graph? 20. And who gets paired with who there? Who does Brad get hooked up with? Jen. And that leaves Billy Bob with Angelina. And the weight is 20. So even though Brad really likes Angelina, if I go that route, my weight is 21, which is not as good. So the min-weight matching would be this one. Okay, now it turns out that finding the maximum matching, the maximum number of edges you can put together, or finding the minimum weight perfect matching, those are both solvable, tractable problems. You don't get $1 million prize for solving that. The algorithms run in, quadratic to cubic time, so not terrible. But they're not NP complete, so people know how to do it. Now, they are pretty complicated, so we're not going to cover them in 6042. What we're going to do is look at a slightly different version of the problem that actually turns out to be more useful in practice because there's a very nice algorithm for it. Now, in the version of the problem that we're going to look at, everybody has preferences, a preference list. It's not weighted, but it's a priority order of who they want to get mated to or matched up with. So it would look not quite like that, but it would look like this. So Brad, Billy Bob, Jennifer, and Angelina, same players. But what we do is we know that Brad really likes Angelina, and Angelina really likes Brad, so they're first choices. At least was. Number 2 for Brad is Jennifer, but Jennifer really likes Brad first, and Billy Bob second. Billy Bob likes Angelina first, then Jennifer. Angelina thinks Billy Bob is number 2. So it's not necessarily symmetric. Jennifer has Brad as the first choice. Brad has Angelina as the first choice. All right, so it's an asymmetric situation. Now, what would happen if we set up our marriages so that Brad's married to Jen and Billy Bob is married to Angelina? What might happen if we made those as our pairings and we put them on a desert island, all 4 of them? What's likely to happen there?
Cheat on each other.
Yeah, we're going to have a problem because Brad and Angelina have the hots for each other here, and they like each other better than their spouse. So before you know it, they're going to be doing their 6042 homework together late at night. All right? Now, when this happens, we have what's called a rogue couple. Given a matching X and Y, a boy and a girl, say, form a rogue couple. If they prefer each other over their mates. In M. All right, so here, if we married Brad to Jennifer and Billy Bob to Angelina, Brad and Angelina form a rogue couple because they like each other better than who they were hooked up with. And that's sort of a bad thing. It creates instability if you were to make the matchings that way. In fact, we say that a matching is stable if there aren't any rogue couples. And now, one thing to make clear is that your preferences can't change over time. So it's not a situation where you get bored with your spouse and you change your mind and then you go off and create a rogue couple. You're fixed in your preferences over all time, and you know playing the field, none of that stuff here. Okay, so it's fixed once and for all. And your goal, of course, is to create or find a perfect matching that's stable. That's the goal. So get everybody married up and make it stable. All right, is it doable in that example? If I put those 4 people on a desert island, could I make a stable matching? Yeah, who would I match Brad to? All right, good. And then Billy Bob gets Jennifer. Now, I'm not saying that you make everybody happy, right? Because Billy Bob and Jennifer are probably not happy there. They each got their number 2 choice, but it's stable because Brad and Angelina aren't going anywhere. They're going to stay together because they like each other best. And so there's no chance that that Angelina's going to sneak off, with Billy Bob, or that Brad's going to sneak off with Jennifer. All right, so it's stable. Not everybody's happy, but it's a stable set of marriages. Okay. Any questions about what we're trying to do here now? Yeah. That's a great question. You'll see it referred to both ways. Technically, it's a subgraph, so it has nodes and edges. But you'll see me and you'll see everybody say, oh, it's a bunch of edges that don't share any nodes. And you'll see them refer to it as the edges. But really underlying that, it's a subgraph, technically. Any other questions about what we're trying to do here to find stable perfect matching? All right. Well, in this example, there was a stable perfect matching. But what about in general? If I have a lot more people and they have arbitrary preferences, how many people think you can always find a stable perfect matching? Well, there's one optimistic person. How many people think there's some cases where you're just not going to be able to do it? Wow. Okay, so pessimistic view. Well, in some sense, you're both right. If you allow boys to prefer boys and girls to prefer girls, then it is not possible. And I'll give you an example. You can find examples where there's always a rogue couple. But if you require boys to only get matched to girls and vice versa, then it is possible to always find stable marriages, stable matchings. All right, and we're going to talk about an algorithm for that. But before I show you the algorithm, let me show you the bad case when boys can prefer boys, or it's sort of a unisex scenario. So here's a bad example with 4 people. And the idea is to create a love triangle. So we have Alex, who prefers Bobby Joe. Bobby Joe prefers Robin. And Robin prefers Alex. And their second choices go in the opposite order there. All right, so Alex wants to be with Bobby Joe wants to be with Robin wants to be with Alex, and then there's Murgatoid. And nobody likes Murgatoid, so that's choice 3 for all of them here. And Murgatoid's choices, preferences don't really matter in this case. Hope nobody's named Murgatoid in the class. I'll get complaints here. All right, so I want to claim and prove a theorem that says there is no stable matching for this group of preferences. So we'll state that as a theorem. There does not exist a stable matching for this graph. The proof is by contradiction. Assume there is one. All right, so assume there exists a stable matching. We're going to find a rogue couple in it. So call the stable matching M. Well, if there's a stable matching, Murgatoid's got to get married to somebody. Murgatroyd will be matched with someone all right, now here I'm going to do something that you can do in your proofs, but you got to be careful when you do it. I'm going to say, without loss of generality, assume Murgatroyd is matched to Alex. All right, and I can do that, so this is the abbreviation, without loss of generality, by symmetry. And really, I should explain what I mean here in the proof. Well, that love triangle is symmetric. Each one has a preference to the next person around the triangle. You know, in terms of graph isomorphism, with the weights on that, every node looks the same, so I can use symmetry. So we're going to say, without loss of generality, we're going to assume Murgatroyd is matched to Alex. And I'm implying the argument is going to be the same. What I say next is the same no matter who Murgatroyd is matched to, because it's symmetric. All right, if Murgatroyd is matched to Alex, do you see a rogue couple up there? So you'd have Robin matched to Bobby Joe. Murgatroyd is matched to Alex. Alex and Bobby Joe. No? Alex and Robin, yeah. Alex and Bobby Joe aren't rogue because Bobby Joe likes Robin. Likes the person he or she's married to. All right, so they're not going to go off with Alex. But Alex and Robin are a rogue couple because Robin likes Alex the best, and Alex for sure likes Robin better than Murgatroyd. All right, so they both prefer each other to their mates. And so they form a rogue couple. All right, so Alex and Robin form a rogue couple, and that means that M was not stable. The matching was not stable. And that's a contradiction, because we assumed it was. So we have a contradiction, and the proof is done. Any questions about that? And I'm sort of implying here that you could match, could have had Murgatroyd matched to Bobby Joe, and then Bobby Joe and Alex would have been a rogue couple, or Murgatroyd matched to Robin, and then Robin and Bobby Joe would be a rogue couple, either without loss of generality. So it's OK to use that, but you want to be careful that you're doing it OK. Questions? Yeah.
So without loss of generality only works if it's like perfectly symmetric?
Yeah. That basically the argument you're going to make is just going to be the same argument done in all three cases. And to save yourself some effort, you're saying don't do the three cases, do one. The other two look the same. So technically, you could add case 1, case 2, case 3, and they would have looked symmetric. OK? All right, now, this is not very surprising. As you all voted, almost all of you said it's hard to find stable matchings. You might not be able to do it always. And in fact, you can't in the unisex world. The surprising thing is you can always find a stable matching in the world where boys can only be paired with girls and vice versa. Now, this statement, this result is pretty famous. The problem itself is known as the stable marriage problem. So let me just define it here. And then we'll talk about an algorithm to find the matching. So we have n boys and n girls. And it's important we have the same number of each. Now, actually, tomorrow in recitation, you're going to look at the scenario where there's more girls than boys, or vice versa. And you'll be using a similar algorithm, but it'll be a different context. And that's the context that comes up in matching interns to hospitals and stuff like that. But for our version, it's an equal number of boys and girls. Each boy has his own ranked preference list of all the girls. So every boy sort of has his dance card of the girls that he likes in order. All right, the orders can be different for different boys. And each girl has the same thing. She has her own list, ranked 1 to n, of all the boys. The lists are complete, and there's no ties. So all the ties have to be broken here. And the goal is to find a perfect matching without rogue couples. Okay, so let's try an example. Before we do the algorithm, let me just do a bigger example with 5 boys and 5 girls. And we'll get some feel for this is not completely obvious how to find it. Okay, so let's put the boys over here. And here's boy 1. And his preference list is going to be the girls will be C, B, E, A, D. And boy 2 is going to have the preference list A, B, E, C, D. And boy 3 is going to have D, C, B, A, E. Boy 4 is going to be A, C, D, B, E. And boy 5, I'm going to have to write his across like this, A, B, D, E, C. And the girls also have their lists, so let's put those up. So girl A likes the boys in order 3, 5, 2, 1, 4. Girl B likes them in order 5, 2, 1, 4, 3. Girl C has the order 4, 3, 5, 1, 2. Girl D, 1, 2, 3, 4, 5. And then the last girl E has 2, 3, 4, 1, 5. All right, so say that's our matching problem, and those are the preference lists. Any ideas for how we might try to make an algorithm to do this? Any thoughts about what you'd do? What are some approaches we could take? Yeah? Use the greedy algorithm. Oh, the mating algorithm. Well, yeah, the mating algorithm is going to do very well. But I haven't told you what that is, and it's a little complicated. So I sort of want to explore the things you might know from what we've done so far. What approaches have we seen so far for solving problems? Yeah? The greedy algorithm. Yep, and let's try that. So let's choose the first boy, and we'll just go down and give each boy the best choice available and see what happens. First thing to try usually is the greedy algorithm, and about half the time it'll work in life, and half the time it won't. So let's try greedy. So boy 1 is going to get his first choice, girl C? Who does boy 2 get? A. Who does boy 3 get? D. Oh, this is going well. Who does boy 4 get? Boy 4, yeah, boy 4 has got to go all the way down to B because A, C, and D got taken, so boy 4 gets B. And boy 5, who's left? E, fourth choice again. All right, well, maybe that's a stable matching. All right, well, let's see. To see if it's stable, we got to see, are there any rogue couples? Well, is there any rogue couple involving boy 1? No, boy 1 got his first choice. He's not going anywhere. Boy 2? No, first choice. Same with boy 3. These boys are quite happy. They're not doing anything. Boy 4 may not be so happy, though, because boy 4 got paired with B. So there's possible rogue couples. Let's see, is 4A a rogue couple? No. A hates boy 4. Right? No chance she's running off with boy 4. So, 4C. All right, let's see that. Where's C? Oh, yeah. C has the hots for boy 4, so she likes him better than whoever her mate was, and boy 4 likes C better than who he got matched with, boy B. That is now a rogue couple, so the greedy algorithm did not work. That's too bad. Well, it would be a short lecture, I guess, if it worked. Well, what would you do next, sort of, if you were? I mean, you could try to match 4 with C, and then try to patch things up, and you could start doing that, but you might create other rogue couples. In fact, I don't know of an approach. Yeah.
You could let it evolve and see if it gets anywhere stable.
Say it again.
You could let it evolve and let all the rogue couples go off and see if it ends up anywhere stable.
Yes, you could start swapping around to get rid of rogue couples. In doing that, you might create other rogue couples. In fact, I don't know of an algorithm that works like this, that's known to work, where you start patching things up, because as you're patching things up, you might make other things much worse by doing that. So I don't know of an approach that way. What's another approach? Yeah?
Pertaining to what order they have each other.
And then do
the highest order and pair them up.
min-weight matching kind of thing?
Maybe.
Maybe? I don't know of an approach like that works. Also, min-weight matching, that algorithm is going to be more complicated than the one I'm going to show you in the end. It takes more time to run. And I don't even know if it works. Like, I don't know if you can take these numbers and make weights on the edges to get a min-weight matching. Oh, a merge sort. So you take the minimum weight edge, put that in, and recurse on that kind of thing. I don't know. It's possible. In fact, a recursive approach is a good idea. I don't know of a nice recursive algorithm for this. It's true that if you found a boy and a girl who liked each other best, you could then match them safely and recurse, because you know they're not going to be in a rogue couple because they like each other best. Then you could recurse. But that might not exist here. You might not have a boy and girl that like each other best, in which case it's hard to know. I don't know now if you pick the minimum weight in some sense, like add the preference list or something to make a min weight and recurse on that, if that works. I don't know of an approach like that. But those are the kinds of things you try. And as far as I know, all those simple things fail for this problem. But there is something that's a little more involved, but does work. And that's the mating algorithm. And does everybody have the handout? It's back up there. I got some copies down here if you need it. But pull that out. So we're going to read this and talk about what the algorithm is and then prove that it performs well. So the initial condition is you have each of the n boys has an ordered list of the n girls and vice versa. And the ritual, we're going to view this as a mating ritual, and really the program is doing it, the code's doing it, but think of it as real life. It takes place over several days. Now, the day is broken up into 3 parts: the morning, the afternoon, and the evening. And in the morning, each girl comes out to her balcony and stands on the balcony. Each boy goes to the balcony of his favorite girl who is still on his list, that hasn't been crossed off. Now, initially, every girl's on his list, so he goes to his favorite girl, goes under her balcony, and serenades her. Now, if over the course of the algorithm the boy has nobody left on his list, he's out of luck. He just stays home and does homework. All right? There's no serenading anymore for him. Now, in the afternoon, the girls who have at least one suitor, a boy down there serenading her, looks at all the suitors, picks her favorite, and to the favorite she says, maybe I'll marry you, come back tomorrow. Girls don't want to make it too easy here for the boys. Now to all the other boys who are lower priority, she says, I will never marry you, go away. So she writes them off for good. Now that night, any boy who heard a no, like the girl said, no, I'll never marry you, crosses that girl off his list. Because, it's the only practical thing to do at that point. Now, if the boy heard the maybe I'll marry you, well, he's going to go back tomorrow because that's still his favorite girl that's not crossed off. So he goes back and serenades her again the next day in the hopes that eventually she'll say yes. Now, we keep doing this every day, okay? And if we ever encounter a day where every girl has at most one suitor, the algorithm stops. And then every girl who has a suitor says, yes, I will marry you. Now, if a girl doesn't have a suitor, there's no one to marry her. Now, we're going to prove that doesn't happen. Okay? But the termination condition is you no longer have a situation with two or more boys under one balcony. Okay? All right, so let's run that algorithm on this example. Just so we make sure we understand it, because then we're going to try to prove theorems about it. So here are the serenades that are going on. And here's the girls and the days. It's going to work over 4 days in this case. And then we're also going to keep track of the boys' list, who's gotten crossed off. All right, so these will be the crossouts down here. Actually, maybe I'll fit it up here if I can. Girls, let's see, A, B. No, I'm going to have to space it out. And the boys had their lists here. And we have boys 1, 2, 3, 4, 5. And here I'm going to record the crossouts. All right, so let's look at day 1. Who is under girl A's balcony on day 1? 2, 4, and 5 each like girl A the best. So she's got a lot of activity. These 3 boys show up. Anybody under girl B's balcony? No, nothing there. C. Does C have anybody? Boy 1, yeah. D, 3. And E, I don't think there's any action, right? Nope. All right, so that's the status on day 1. So the action's all up here. Right? So what does girl A do? Who does she tell to hang around? Number 5. Yeah, she's got 5, 4, and 2, and she likes 5 the best. She tells 5 to come back, and she says to these guys, we're not going to marry him. That means that boys 2 and 4 cross girl A off their list. So they say A is no longer possible for them. All right, now we go to day 2. And 5 goes back to girl A, and of course, boys 1 and 3 stay there. Where does boy 2 go on day 2? B. All right, so boy 2 shows up here on day 2. And let's see, boy 5 is already there. And then we got to get boy 4. Where does he go now? C. All right, boy 4 shows up here. All right, so now the action is with girl C. And what does she do? Yeah, she keeps 4, and she boots poor 1. You know, let him along for a day, and then he gets the boot because boy 4 showed up, right? Because girl C likes 4 better than 1. So bad luck for 1 there. So now 1 goes home that night and crosses off girl C. Okay. All right, and where does 1 go on day 3? All right, so he goes to, crossed off C, goes to B. All right, so this is left over. We have 5, 2, 4, 3. Boy 1 now goes to B, right? Okay. And then what does girl B do? Who does she keep around? Keeps 2, boots poor 1. All right, so 1 says, all right, I'm crossing B off my list. Got the message. And now where does boy 1 go on day 4? E, third choice. Okay. So 1 shows up down here, and these guys keep returning. Wow, so on day 4, there's no more fighting. Every girl has at most 1. The termination condition is invoked, and these are the marriages that take place. The girls say yes. All right, now does everybody understand the algorithm we used? Any questions on the algorithm? Yeah? That's in case the algorithm doesn't work, because we haven't proved it works yet, and I got to have a possibility for a boy crosses every girl off his list. He gets rejected everywhere. That is a possibility, so I got to say what would happen in that possibility. Now, we will prove in a few minutes that condition never arises. Okay? But I'm giving you what might happen, and which so it never does. So no boy ends up having to stay home and do homework here. All right, so that's the algorithm. Now we got to, let's see if we can see if there's any rogue couples. All right, so for example, let's look at boy 1. Boy 1 got paired to his third choice, E. So 1C might be a rogue couple. Is that possible? No, because C got 4 here, which is her first choice. She's not going with boy 1. That's not working. What about 1B? Could that be rogue? No, B got 2, and B likes 2 better than 1. So 1C and 1B are not rogue, and 1 got E, so there's no other possibility for boy 1. So boy 1 is not in a rogue couple. What about boy 2? 2 got B, and that's 2's second choice. What about 2A? Let's see. A got 5, and A likes 5 better than 2. All right, so that's not rogue. Boy 2 is not rogue. All right. Boy 3. Boy 3 got his first choice, right? 3 got D. So 3's not going anywhere. Boy 4 got, who did boy 4 get? Got C. 4 got his second choice. What about 4A? A hates 4. A's not going to get caught dead with 4, so that's not rogue. So 4 is okay. 4 is not in a rogue couple. And finally, boy 5. Boy 5 is paired with A, and that is boy 5's first choice. So he's not wandering off here. All right, so in fact, we've just argued that this is a stable marriage, set of marriages, a stable matching in this case. Any questions now about what we're trying to do? Okay, because we're going to try to show now it always produces a stable matching. And to do that, we need to do a few things. All right, so what are the things we need to show to prove everything is going to be good here? What are some facts we need to prove? Yeah? Yes. The algorithm terminates. So we need to show that the marriage algorithm, TMA, terminates. You know, otherwise the boys are serenading forever, and that's not too good. All right, what else do we want to show? Yeah?
If it does terminate, then one is left empty.
Then
Everyone gets someone.
everyone gets married. Yeah. Stability is easy if nobody gets married. All right. What else do we want to show here? Yeah. There are no rogue couples. All right. What else might we like to show? These are the three main ones. There's a couple other things you might like. Yeah.
It runs quickly.
It runs quickly. All right, you can only serenade for so long. All right, in fact, it does run quickly, and that's why it's useful in practice. Anything else you might want to show about this algorithm?
How many people you crossed out?
How many people you crossed out? And that'll go to, yeah, you could, and that'll tie into how long it takes. Yeah? Anything, yeah?
Average likeness between the couples.
The average likeness. Oh, so, yeah, we haven't had a notion here of how happy people are at the end, because we don't have a weighting on the edges. But you might want to think about that. That's actually a good point. Yeah?
If it matters who serenades and whether the girls or boys get it.
That's a great point. Is this algorithm good for girls or good for boys? Yeah, that's a good point. Fairness. All right, so we'll take a look at fairness also. Is it better to be a serenader or be on the balcony making your choices? Okay, so this is what we got to do. So let's start by showing TMA terminates and that it terminates pretty quickly. Now, in fact, I'm going to prove a fairly crude bound on the time, but it actually does fairly well. So our first theorem is going to be that TMA terminates in, at most, n squared plus 1 days. N is the number of boys and girls. The proof is going to be by contradiction. This is probably the only day where we'll do a bunch of proofs and none of them use induction. They're pretty much all by contradiction. Suppose TMA does not terminate in n squared plus 1 days. Because we're going to show that leads to a contradiction. We need to show that some kind of progress is made each day to show that it terminates. Yeah?
We can keep account of the number of crosses that have totally happened. So
Yeah.
if it has not terminated, then at least one girl is saying a no to at least one guy.
Yes.
So the number of crosses cannot be infinite, so it must end sometime.
Very good. Okay, let's take that as a claim. And you've given the proof of the claim, which is great. If we don't terminate, on a day, that must be because a girl had 2 boys there or more, therefore she rejected some, at least one, and that night the rejected boy crosses a girl off his list. So if we don't terminate, then at least one boy crosses at least one girl off his list. And so we're going to measure progress by the crossouts. So every day we don't terminate, a boy crossed a girl off his list. So if we didn't terminate in n squared plus 1 days, we must have crossed off n squared plus 1 girls across all the lists. Well, is that possible? To have done n squared plus 1 crossouts? What do you think? How many names are on each list? N. And how many lists are there? N. So there's n lists with n names. Implies there's at most n squared crossouts ever. But we just said we had n squared plus 1 crossouts. All right? But we have also n squared plus 1 crossouts. And that's a contradiction. All right? So we're done. It has to terminate within n squared plus 1 days. Any questions? This is a very common proof technique in computer science. You're analyzing some system, and every step or every day or every time period, you want to argue progress got made, and then after you've made enough progress, you have to be done. And therefore, the algorithm is completed. All right, so we know that TMA terminates. Now, we still got to get everyone married and have them all be happy, or at least stable. Now, to do this, we're going to use an invariant. Yeah?
If a girl has some guy in front of a balcony on some day, then she will always have at least one guy in front of her.
That is true. Something even stronger is true.
Or a better guy.
Have a...
Like if she has a preference for someone, like someone rank 5, then over the period, only better guys.
Yeah, that's a great invariant. As the girl is sitting there on her balcony, things only get better. Because she always keeps the best one around that's there. And when new ones come in, they got to be better than the last one for her to keep them. So as she rejects boys, she only does that because she's got better ones there. And whoever she says maybe to always comes back. So an invariant of this algorithm is that when a girl has a suitor, going forward, she only has suitors she likes at least as well. And if she ever rejects a boy, then she's got somebody better there forever. All right, so let's state that as an invariant and prove that. Okay, so we're going to let P be our invariant here. P is the statement that if a girl, G, ever rejected a boy, B, then the girl, G, has a suitor, or if the algorithm is terminated, a husband, who she prefers to be. All right, that's going to be our invariant, and now we got to prove it's an invariant. So we'll do that with a lemma, call it lemma 1. P is an invariant for TMA. All right, let's prove that. Now, what's the first thing you got to prove when you're proving something as an invariant? There's two things you got to do to establish an invariant. What's the first one? Base case. Show it holds true at the beginning. Proof is going to be by induction. And so we got to show that P holds true at the beginning. But what are we going to induct on here? What's the parameter we're inducting on? Time. The number of days. Good. The base case is day 0, the beginning. All right. Well, is that statement true on day 0? Yeah, it's true for sort of a weird reason. Nobody's been rejected yet. So it's what's called vacuously true. Because there is no girl G has rejected any boy. So it's true. Okay? So no one is rejected yet. So it's vacuously true. All right, next we have the induction step. Now, so we'll assume P holds at the end of day D. And we need to argue that it holds now at the end of day D plus 1. So say it's true up to now, up to day D. Why is it true at the end of the next day? Well, there's 2 cases to look at here, depending on when G rejected B. So if she rejects B on this day, day D plus 1, well, why would she reject B on day D plus 1? There's only one scenario, yeah?
Boy.
There's a better boy. And so she says maybe to him, and he becomes her suitor. So, in fact, P is true. All right, so then there was someone better. And that implies P is true on day D plus 1. Case 2, very similar. It's a very simple proof. G rejected B before day D, before D plus 1. Well, now we use the fact that P was true at the end of day D, which means P now implies that G had at least as good a suitor. Actually, it's better because it was rejected. A better suitor on day D. All right, that's what the hypothesis says, the invariant says. And now we just have to look at what happens on D plus 1. Well, either she has the same suitor on D plus 1 or somebody better came along. And so we're going to be done. She has the same or better suitor on day D plus 1. And that implies P is true on D plus 1. And we're done. All right, so I went through this proof. It was sort of obvious, but this is the careful way you'd write it down to show that the invariant holds. Any questions about the invariant in the lemma? All right, so things only get better for the girls. If she ever rejected somebody, she's got somebody better. So now we can prove the main result, that everyone is married. And again, the proof will be by contradiction. So we assume not everyone was married. Assume for the purpose of contradiction that some boy, B we'll call him, is not married. Because if everyone's not married, then some boy is not. If not everyone is married, then some boy is not married. So when it terminates, B is not married. Well, what do you know about B if he was not married at the end? He was rejected by everyone. Because if at the end he's still under a balcony, if he still had somebody on his list, he'd be there. And he'd be getting married because it's the end. So this means that if B is not married, he's rejected by everybody. Yeah? Oh, he's on everybody's list. Everybody has everybody of the opposite sex on their list, but he had to cross everybody off. That's true. Yeah?
It would mean that everyone had somebody better on the same day that B was there.
That's true. That means that B crossed every girl off, B's rejected by every girl, which means every girl has somebody better than B. Which is not possible because that would mean every girl was married. And therefore, the equal number of boys and girls, that means B would have been married. Good. All right, let's write that down. All right. This means that B was rejected by every girl. Okay, that means that every girl by lemma 1 has a better suitor. And that's where we use lemma 1. And that means that every girl is married. And that means that every boy is married, including B. And that's a contradiction because we said B wasn't married. Okay? Everybody buy that proof? Any questions about that? Yeah, proof by contradiction is a pretty powerful technique. Once you assume something that's not going to be true, it gives you a lot of power to find a contradiction. All right, so now we know that the algorithm ends and everybody gets married. All we got to do is show that there's no rogue couples. So let's do that. TMA produces a stable matching. All right, now how do you suppose we're going to prove this? What's going to be the approach to prove this? Yeah? Assume that there's a rogue couple, that namely this is not true, so there must be a rogue couple. So let Bob and Gail be any pair that are not married. I need to prove that Bob and Gail are not rogue. And then we'll be fine, because it says everybody who's not married is not rogue, then we know we have a stable matching. Now, there's a couple of cases here. Bob and Gail weren't married. So there's two ways that could have happened. What's one of them? What's one reason they might not be married? Something that happened that made that impossible. Yeah?
Gail rejected Bob.
Good. Case one. Gail rejected Bob. Well, what do we know in that case that Gail rejected Bob?
Gail has better suitors.
Gail has another suitor that she likes better. And in fact, what do we know about who Gail married?
Better than Bob.
Better than Bob. Things only get better for the girls. All right, that's lemma 1. All right, so this means that Gail marries someone better, that she thinks is better than Bob. And that's by lemma 1. Well, can Gail and Bob be a rogue couple here? No, because Gail likes her spouse better than Bob, so she's not going to be in a rogue affair with Bob. All right, so that means that Gail and Bob are not rogue. All right, case 2 is Gail did not reject Bob. She never did. That's the other case. She didn't reject Bob. Could Bob have ever serenaded Gail in this case? No, because if he did and he was never rejected, they would have ended up married. All right? So that means that Bob never serenaded Gail. All right, what does that mean about how Bob feels about Gail? Yeah. Yeah. Bob never got far enough down on his list to serenade Gail. He got married before he got down there. All right, so that means that Gail is lower on Bob's list than Bob's wife. And that means that they are not rogue, because Bob likes his wife better than Gail. All right, so in each case, the cases clearly cover everything. Gail rejected Bob or she didn't. Either way, Gail and Bob are not rogue. So that means there's no rogue couples. And that implies M is stable. TMA is stable. Okay? All right, so TMA terminates. Everyone gets married. No rogue couples. Nice algorithm. So we're done. We actually proved it works. One issue left to think about here. Any questions on that before we launch off into the last issue? Yeah? Is it unique? TMA gives you a unique answer because it's an algorithm. It's deterministic. But there may be other stable matchings. Okay, so there's not just one stable matching necessarily. You can make examples with multiple stable matchings. That's a great question. Any other questions? All right. So, oh yeah.
Is there generally any other way to assess optimality besides the fact that it's stable? Or
Yeah, you can make up lots of them. You could put weights on the edges and get a min-weight matching. You could have try to get the perfect matching with the least unfavorable marriage kind of thing. There's a lot of criteria you can make. This one turns out to be useful in practice in a variety of ways that we'll talk about, and also have a nice, fast, simple algorithm that can actually be run in a distributed environment, which is really nice. So it is probably the most practical approach to matching out there. Any other questions? Okay, the last issue, I don't know if you saw the issues up there, is fairness. All right, so who thinks that TMA is favorable to the boys? All right, just a couple. Who thinks it's favorable to the girls? More. That's the common response. Who thinks it's not, you can't even define it one way or the other? It's unclear and hopeless to decide. Okay. Well, it seems like maybe the girls, because they get the best of their suitors. They sit back and they just take the best as they come along. On the other hand, the boys do try to go out and get their first choice. The girls have to wait. and Mr. Right may never come along. The boys are out there, I'm going for my first choice, and they get denied. Okay, they just move right on to the next choice. So this is actually one of these questions that's studied in sociology, in the animal species. Which is better, proposers or acceptors? What's the more powerful result? Who has the better power in courtship? It turns out that we can answer this question in a very clear way and prove it here. And the answer is the boys have all the power here. This is very favorable to the boys. And we'll see why. Now, to prove that, we need some definitions. Okay. So I got to define a couple things here to be able to prove this. The first is for any collection of preference lists, we're going to let S be the set of all stable matchings. Now we know that S is not empty, right? How do we know that S is not empty here? Yeah, because TMA produces a stable matching, so we know that S is not empty. There's at least one. And in fact, there could be many. Now, for each person, P, we define the realm of possibility for P to be the set of mates that you might have in a stable matching. So it's the set Q of people for which there exists a matching that's stable such that you're mated to that person. So I've written this in some, that's sort of complicated mathematics, but somebody is in your realm of possibility if there is a stable matching where you married them. If it exists, there's a stable matching where you could marry them. And this is, vaguely like, you see sometimes you're going out with somebody and your parents say, oh, they're not in your league or something. This is the mathematical formulation for that. That you could get, there is some way in the world to marry everybody up, so it's all stable, and you could be married to that person. Okay? Let's do an example with 4 people. All right, so for example, say we have Brad, Jen, and Angelina again. And of course, Brad likes Angelina and vice versa. Jen likes Brad. And then there's Billy Bob here. All right. Now, Brad is not realistic for Jen. Brad is not in Jen's realm of possibility. Because in any perfect matching where Brad marries Jen, you're going to have a rogue couple. Brad's going to go for Angelina. So Brad is not within Jen's realm of possibility. And similarly, vice versa, Jen is not in Brad's realm of possibility. Because there's no stable matching where they're married in this scenario for this problem. All right? Now that we have that notion, we can define who your optimal mate is and who your pessimal mate is, the worst case. All right, so we define a person's optimal mate is his or her favorite in the realm of possibility. So your optimal mate is not your favorite overall. It's just your favorite among those who are possible, that there is a stable matching, that you could be matched to that person. And similarly, you have a person's pessimal mate is your least favorite from the realm of possibility. Okay, because you have all the people that you might be married to in stable matchings. Your favorite is the optimal, your least favorite is the pessimal. Any questions about that? Does that make sense? And you don't count the ones that you can't be married to, because if you were, it would be unstable. Okay, now we can state the blockbuster theorems here. Theorem 4 says TMA marries every boy with his optimal mate. Theorem 5, probably can guess, TMA marries every girl with her pessimal mate. All right, so it is optimal for every boy. They get the best possible they could have in stable marriages, and every girl gets the worst possible mate. Now, you wouldn't necessarily think that when you first look at that algorithm, right, where the boys are working down their list and the girls are just getting better and better. But that's the case. Now, let's see. I'm not going to have time to prove them both, but I will prove Theorem 5. And I'm going to assume Theorem 4 is true to prove Theorem 5. Maybe we'll do Theorem 4 tomorrow in recitation. I don't know. So let's do Theorem 5 so you can see how this works. The proof is by contradiction. So we'll assume Theorem 4 is true, and we'll prove the proof of Theorem 5. By contradiction. So assume there was a stable matching where a girl got worse off than in TMA. All right? So that's, assume it's not, Theorem 5 is not true, then there's some girl in some stable matching. So suppose, for the purpose of contradiction, that there exists a stable matching call it M, where some girl and she fares worse than in TMA. I want to show that results in a contradiction. All right, and the proof is pretty simple. It's just a simple picture. So G did worse in M than in TMA. All right, so let's let B prime be the mate of G in M. So girl G did worse in M than in TMA, so here's her mate in M. And let B be her mate in TMA. Who does she like better, B or B prime? B, because we're saying that she did worse in M than she did in TMA, so she likes B better. And let G prime be the mate of B in M. Now, who does B like better, G or G prime? G. Not G prime. B got married to G prime in M, but who does, what does Theorem 4 say? Yeah, G. Theorem 4 says that across all the stable matchings, B gets his favorite mate in TMA. So G prime is in the realm of possibility, and so is G. And we know from Theorem 4, B likes G best, better than G prime, because of Theorem 4. So what happened here? There's a rogue couple in M. B and G are a rogue couple in M. And that means that M is not stable. And that is a contradiction. All right? And so Theorem 5 is true. Okay? Because we assumed that we had a stable matching M where there's a girl who did worse off. All right? So it really pays off to be the aggressive party in courtship. Everybody lives happily ever after, especially the boys in TMA. Now, TMA arises in lots of applications. The most famous is the matching program that's used to match MDs to residency programs. So how many pre-meds are here? Well, there's one at least. So you're going to go to medical school someday, and at the end of medical school, there's a big day called Match Day where you get assigned to a hospital for your internship. And the way that works is using this algorithm. And who do you suppose is the boy in this algorithm? The hospital. And they want it so that when they make the matchings, that there's not some pair of an intern or doctor in a hospital where they like each other better than what they got. This is used in online dating for the obvious reasons. And we actually use this algorithm a lot at Akamai to load balance traffic on the web. And here you have the boys are web servers, and the girls are requests for service. And the goals are to balance performance, getting a server that's nearby you that's fast, and on the other side, our cost. And by who we make a boy and a girl, we can trade off cost for performance in a very nice distributed way. All right, so that's it for today.
Okay. First in and the last out. Never tried to go the fast route. Marathon, not a race. Put in hours and I cash out. Game time been lit. Been the man, been him. In the box like 9-9. Got pinstripes on my skin. Okay, go mamba all in my zone. When the wind going home. Hear it all in my tone. Worked hard for this throne. You know I'm never lazy. Nothing faze me. See me win, but those L's made me. Hear him talk, let him talk. All the ghosts have been called crazy. Lights on, I'm on. Lights on, I'm on. Love the pressure, I can't let up. Keep my head up, I can't let up. You know I can't stand still. Sticking to the plan still. No bots on my fans real. Stay true on the man still. Losses got you bent up. All that ain't go pent up. See you in my inbox, but everybody can't come. I worked hard for this, put in hours, got scars from this. No sleep, I just toss and turn, thinking about how hard it get. I've been chilling with my family now. You been chilling with the party is. Put in reps cause they called my bluff. Got one shot to get all these dubs. And we on. Lights on, I'm on. Lights on, I'm on. Love the pressure, I can't let up. Keep my head up, I can't let up. Lights on, I'm on. Lights on, I'm on. Love the pressure, I can't let up. Keep my head up, I can't let up.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So welcome to this week. We're going to talk about trees mainly. we're going to talk about some very special ones, spanning trees. But before we do this, we will go through a whole bunch of definitions, and I will give examples to explain how it works. So let's talk about walks and paths. So you've already seen a bit of graph theory. We talked about graph colorings and so on. But now we're going to talk about special types of graphs and special structures within such graphs. Well, let's start with the first definition. How do we define a walk? Well, a walk is something very simple. You walk from one vertex in the graph over an edge to a next vertex, to a next vertex, and so on. So how do we define this? A walk is a sequence of vertices that are connected by edges. So, for example, we may have something that looks like a first vertex that we call the start, and an edge that goes to a second vertex. We continue like this till we end, say, at vk, which we call the end of the walk. And if we look at this, we say this is a walk from v0 all the way to vk. It has exactly k edges, and we say that the length is actually equal to k. So this is a very basic notion, and what we are really interested in is actually paths. And paths are special types of walks in which all those vertices are actually different from one another. But let's first give an example of a graph that we will study throughout the whole lecture, especially when we come to spanning trees. So let's have a look at the following graph. Actually, let me just like this. So let this be a graph. Then, for example, we can have a walk that goes from this particular edge, say we call this V0. It goes over this edge over here. Suppose I want to end over here. Well, I can go many ways in this particular one. I can go over this edge. I may go over here. I may go all the way to this part over here. I may return if I want to. And then finally I take this edge, for example, back to over this edge. I will end in the last vertex vk. So what we notice here is that we have a walk that actually gets to this particular vertex and then returns to this vertex over a few other edges and then goes all the way to vk. So if you talk about the path, then we really want all the different vertices not to occur twice. So let's define this. So a definition is that a path is actually a walk. Where all edges, where all vertices, vi's, are different. And in this particular case, well, for example, if we strip off this part over here, you will get a path from v0 to here, to here, to here. And all these vertices on the path on this walk are different, and therefore it is a path. This also shows us something. It is possible to construct from a walk a path. As you can see, we started off with this particular walk, and we just deleted, essentially, a part where we sort of came back to the same vertex again. And when we delete all those kinds of parts, we will end up with a path. So can we formalize this a little bit better? Then we get the next lemma. So let's call this lemma 1. And let's see whether we can prove this. So we want to show that if there exists a walk from, say, a vertex u to, well, maybe I should not use arrows. That's confusing. From u to v, then there also exists a path from u to v. So how can we prove this? Do you have any ideas? So what kind of proof techniques can we use here? Maybe one of the principles that we have seen?
I'm not sure which principle it would use, but I have an idea of how you could show this. It's basically if you visit one vertex, let's say you go 1, 2, 3, 4, 5, 3, 6. As a walk from 1 to 6. Then you just take out the 4 and 5. So you just go 1, 2, 3, 6.
Right, so what did we do there? We essentially had a walk, and then we cut out a smaller part here that recurs in a sense. And we have shortened the path, we have shortened the walk to a smaller path. So what we have used here, that we can sort of take out parts of the walk, just like what we did over here, until the walk gets shorter and shorter and shorter. So maybe one of the things that we may consider is a walk of shortest length. So, and we know that this is possible. Oops, sorry about that. So let's prove this. So, for example, suppose there exists such a walk from u to v, then we know by the well-ordering principle that there exists a walk of minimal length. So that's what we're going to use here. And then we're going to essentially go in the same direction as what you were talking about, because we're going to show that it's not possible to delete anything more, because otherwise, if you could do that, the walk would get shorter, and that's not possible, because by the well-ordering principle, we simply consider that there exists a walk of minimal length that we are interested in. And we will show that this particular walk is actually going to be a path. So let's see how we can do this. So let the walk be equal to, well, it starts in v0, is equal to u. There's an edge to say v1, goes all the way up to vk, which is the last vertex, v. So what are we going to prove? We're going to prove that this is actually a path. And since this is a walk of minimal length, well, suppose it is not a path. So we are going to use contradiction. Well, if it's not a path, then by our definitions over here, there must be two vertices that are actually the same, just like in here. So we go from v0 to, say, this particular vertex, to this one. And then we come back to this one, and then all the way to vk. So if it is not a path, then two of those must be equal to one another. And then we're going to use this trick. We're going to take out this part. We get a shorter walk. But that contradicts that our walk is minimal length. So that's sort of the proof technique that we are doing. OK, let's do this. So, well, first let's consider a few cases. If k equals 0, then that's pretty obvious. We have only a single vertex u that is connected by a zero-length path to itself. So this is fine. For k equals 1, we have just a single edge. And then we're done too. That's a path as well. So let's consider the case where k is at least 2. Well, suppose that the walk is not a path. So we are going to assume the opposite. If it's not a path, then we concluded that two of those vi's must be equal to one another. So there exists an I unequal to j, such that vertex vi equals vj. But now we have a walk that goes from v0 all the way to, say, vi, which is equal to vj, and then we go all the way up to vk, which is equal to v. So essentially, we have created a shorter walk. We have taken out this little triangle over here. Now this is a shorter walk, and this contradicts our assumption of minimality. So that means that our assumption over here is not true. So the walk is actually a path. So this concludes the proof. So even though this lemma is pretty straightforward in the sense that we all feel that if you have a walk, then you can create a path, if you really want to write it down with all the principles that we have been taught, you can see a few things appearing here. So we first started with the well-ordering principle, and also we used the method of contradiction in our proof. Okay, so let's talk about the next definition. So we talked about walks and paths. Let's talk about connectivity. And we actually define two vertices u and v to be connected if there is a path that connects u to v. So u and v are connected. If there is a path from u to v. And now we can talk about graphs that are connected. That's a very important concept. A graph is connected if every pair of vertices is connected. So when every pair of vertices in the graph are connected. So an example is that particular graph on the blackboard. You can see here that there's always a path to be found from this vertex to this one or to that one, to this, to that, to this or that. You can do this for any two vertices. So this is a connected graph. A graph that is not connected looks something like this. For example, you may have a single edge plus, say, another triangle, maybe with another edge or something like that. So they are disconnected from this vertex. I do not have a graph that connects to a vertex over here. Okay, so this is about connectivity. And now we can start talking about cycles and closed walks. And together, these concepts will help us to define trees. And then we can start talking about this very special concept, spanning trees. Okay, so let's see how that works. So cycles and closed walks. We first define a closed walk, and once we have done this, we are able to get into cycles. So what's a closed walk? Well, it's actually a walk for which the start and the end vertex are the same. So it starts and ends at exactly the same vertex. So this is all pretty straightforward. So we have V0 connected to, say, V1, all the way up to Vk. And Vk itself is equal to V0. So you have a walk that goes all the way from V0 all the way back to Vk. For example, in this graph, you could have walked all the way back to V0, and you would have a closed walk. So what's a cycle? A cycle is a little bit more special, in which all these vertices over here are actually different from one another. So if k is at least 3, so the walk is not just a simple edge or just a single vertex. And if all V0, V1, all the way up to Vk minus 1 are different, then we are saying that we have a cycle. Then it is called a cycle. Okay. So these two concepts, connectivity and cycles, will help us to define trees. So what are trees? A simple example is something that looks like this, for example. The idea is that a tree is both connected and it has no cycles. So in this case, we can see that every vertex is connected to every other vertex, but there is no cycle like a triangle or something that is connected all around. So let's define this properly. A definition is that a connected and acyclic graph is called a tree. All right. And within trees, we also have something very special that we call leaves. Leaves are exactly those nodes that have degree 1. So for example, this node has degree 1, right? It has only this edge connected to it. So this is called a leaf. This one also is a leaf because it has just one edge connected to it. But this leaf over here has 3 edges, so it has degree 3. This one has degree 4. This is a leaf again, this one is a leaf, this one, and this one. So this is a very important concept. We often use leaves in our proofs, and we will get to one. So a leaf is a node with degree 1. In a tree. Okay, great. So now let's have a look at the trees. Suppose I'm looking at a subgraph of a tree. What can we say about a subgraph? What kind of structure does this have? So suppose, for example, I would take some connected subgraph. So that's what I'm actually interested in. So for example, I take this, suppose I take this connected subgraph. Then what does it look like? Do we see some structure in this? It's, no?
It's a tree.
Yeah, it's a tree. So are we able to prove this also? So let's, so this lemma we will actually lose later on. So any connected subgraph of a tree is a tree. And the proof, well, how can we start out a proof? Any suggestions? So let's have a look here. So how may I think about this? Well, I may take a connected subgraph, and I want to show, of a tree, and I want to show that it is a tree. A general method could be, for example, to
one of the conditions is it has to be acyclic. So since you're not adding nodes and you're not starting with any cycles, you can't create a new cycle?
Yeah, I think you're saying something like, if I have a connected subgraph, which is like a smaller part of the tree. Now suppose that would not be a tree, say it would have a cycle, then that cycle would also be present in the tree itself. And that is not really possible because a tree has no cycles. So that's sort of indeed how the proof goes. So we essentially use contradiction. And so let's suppose that this connected subgraph is actually not a tree. So suppose that the connected subgraph is not a tree. Well then, in that case, it must have a cycle, right? Because a tree is something that is both connected and has a cycle, and is acyclic. We have a connected subgraph, which is not a tree, so it must have a cycle. Okay, so it has a cycle. But now, since it is a subgraph of the bigger graph, we know that the cycle must also be in the whole graph. So the whole graph has this particular cycle. But wait a minute. The whole graph is the tree. And a tree is acyclic, so we get a contradiction. So that means that our original assumption that it is not a tree is wrong, so it is a tree. So this is, again, such a general kind of proof method that we repeatedly use here. Okay, so this lemma, which we will call 2, we will use in the next proof, where we're going to talk about the relationship between vertices and edges within trees. So, and it's a very a beautiful relationship. The lemma states that if you have a tree that has n vertices, then it must have n minus 1 edges. So there's a very tight relationship here. So a tree with n vertices has n minus 1 edges. So let's see, how can we prove this one? Any suggestions? So what did we use at the beginning of the course here? So we have n vertices, and we want to show that it has n minus 1 edges. We can use induction, right? So let's use induction on n. So how do we proceed if you do this? Well, we always start out with an induction hypothesis. So the statement here would be something like, well, there are n minus 1 edges in any n vertex tree. And if we start with induction, we always start with the base case, right? So we have the base case. So how does this work? So for example, we want to consider P1. So there are 0 edges in any one vertex tree. Well, that's true, right? I have just one vertex. There's no edge. So this is definitely correct. So that's easy. So let's prove the other part, which is the induction, the inductive step. An inductive step is so to do the inductive step, we're going to always assume, right, Pn, and then you want to prove Pn plus 1. So let's do this. So we have the inductive step. And we always start out the same way. So we suppose of n. And now we want to prove Pn plus 1. So how do we do this? Well, take a tree that has n plus 1 vertices. And we want to show that it has n edges. So take any such tree. So let T be a tree that has n plus 1 vertices. So how can we use the induction hypothesis here? So do you have any ideas over here? So I have a tree with n plus 1 vertices. And if I want to be able to use this induction hypothesis, then I can only apply it on trees of, that have n vertices. So somehow I have to delete one vertex, right? So what kind of vertex can I delete in such a way that we still have a tree? And I need that because this induction step can only be applied to trees. So what type of vertex can I remove from a tree and it still stays a tree? So for example, if you look at this example up here, what kind of vertex can I remove here? Yeah, exactly. I can remove a leaf, for example, this one. And why is that? Because it has only one edge connected to the rest of the tree. So if I leave it, if I delete it, I will actually keep a tree. So that's how the proof will continue. So we take out one vertex. So let V be a leaf of the tree. And let's remove this particular vertex. So what do we get? Well, we again have a connected subgraph. So this creates a connected subgraph. And we also know that this is a tree. So how can we conclude that? Well, we had another lemma somewhere. It's behind this blackboard. That says that if we have a connected subgraph, then we still have a tree. So that's great. So this is also a tree. So now we can apply Pn, because we have n vertices, because we deleted one. So by Pn, we can conclude that this particular subgraph has n minus 1 edges. We simply apply our statement over here. So, but we want to say something about the original tree. So how do we do this? Well, we have to somehow reconstruct this tree. Well, we have deleted V, so we have to reattach V again. So let's do this. So we reattach V. And if I do this, well, let's look at this example over here. I reattach the leaf. I will add one more edge. So if I reattach this particular leaf, I will get back the original T over here. And how many edges does it have? Well, it has these n minus 1 edges, plus the one edge that is needed to reattach the leaf. So that's altogether exactly n edges. So now we have shown that for every n plus 1 vertex tree, every such tree has n edges. So now we're done, because this shows Pn plus 1. So this is how the lemma is proved, and in the homework you actually use this. Okay, so let's now talk about very special trees, spanning trees. Now I think this is a very exciting topic. So let's look at this particular graph over here. And let's define spanning trees. So what's a spanning tree? A spanning tree is a subgraph of a graph that somehow spans all the vertices within this graph. So it's a tree that touches every single vertex. So for example, we may have, maybe this is not such a bright color, maybe this one. So for example, we may have a tree that looks like this. So in this particular graph, we can create a subgraph with the thickened green edges over here, which is a tree and also covers all the different vertices of the original graph. This is actually pretty amazing that you can do this. You can actually create such a kind of a tree. And what we want to prove, first of all, is that for every connected graph, we can construct such a spanning tree. So let's first define this, and then we will prove this theorem. And then after this, we're going to talk about weighted graphs. That will lead to minimum weight spanning trees. And then it gets really interesting because we want to figure out how we can actually construct those for any graph. Okay. So let's define a spanning tree. A spanning tree and we abbreviate this as SD, of a connected graph is actually a subgraph that is a tree. So that's the first condition. And it also covers all the other vertices. So it has the same vertices as the graph. Okay. And over here we have this example. So now what we want to show is the following theorem, that any connected graph actually has such a spanning tree. So the theorem is every connected graph has a spanning tree, and let's think about a proof together. So, for example, you know, we may start with the idea to use a contradiction. Suppose there exists a connected graph that has no spanning tree. So how would we go ahead? So how can we prove that there is that we have a contradiction here? So the proof that we're going to propose here is by contradiction, and that means that we're going to assume the opposite. So assume that we have a connected graph. Connected graph G. That has no spanning tree. So how can we use this? How could this be strange? Or what can we do here? Well, yeah. So one of the nice things about trees over here is, so that maybe gives us some insight, is that if we have a tree, well, it seems like such a kind of spanning trees, like is a solution to a subgraph that is connected with a minimum number of edges. Like if I have any other type of subgraph, for example, if it has cycles, I can always remove an edge, of course. So we know that a subgraph of G that touches all the different edges and has a cycle can get shortened by eliminating one edge of a cycle that's within such a subgraph. So maybe we have an idea here, and maybe we can use this. So maybe we can say, let's consider a graph T. So let T be a connected subgraph of G, but with the property that it has a minimum number of edges. So let this be a connected subgraph of G, and we assume that it has the same vertices as G, of course, and in addition, it has the smallest number of edges possible. Okay. So what do we know? Well, let's look at our assumption here. We said that a connected graph, G, that's what we consider here, for which, well, there is no spanning tree. So what do we know? We know that this particular T over here can definitely not be a spanning tree, because that's what we assume here. So can we use this? So let's think about this. So if it is not a spanning tree, then what must it have? So we already know that T is a connected subgraph of G with the same vertices of G. So the only difference between a spanning tree and T is that the spanning tree is a tree, and T is not a tree. So therefore, T must have a cycle. So we use our assumption over here. We know that T is not a spanning tree. And now we can conclude that it must have a cycle. So now we can start thinking about this cycle, and let's feel what can we do here. So we constructed T as the subgraph that has the minimum number of edges possible. So now if we have a cycle, the whole idea is that we're going to delete one of the edges of the cycle. And if we do that, we will be able to construct a smaller subgraph T, essentially, with a smaller number of edges. And that contradicts this particular statement over here. So that's sort of how we go ahead. So if it has a cycle, let's write it out. For example, here we have a cycle, like this. Well, let's prove that if we remove one edge of the cycle, that we still have a connected subgraph. So the whole graph, T, is much bigger, right? It has lots of connections and so on. Suppose we will remove this particular edge over here. So we remove this one. Do we still have a connected subgraph of G that covers all the vertices of G? Well, of course it covers all the vertices of G because you only remove an edge over here, so that's fine. All these parts are still connected to the rest. If we can show that it is connected, well, then we just, we removed one edge, so we actually created a smaller graph, and then we get contradiction, and then we're done with our proof. So let's see whether we can prove that if we remove this particular edge over here, that we still have a connected subgraph. So how can we do this? Well, let's take, so the first case would be if a vertex x is connected to y. So I want to take any pair xy of vertices, and suppose that the path that connects x and y does not contain this particular edge e that I remove here. So suppose this does not contain e. So I look at the graph T. I know T is connected. So I take a pair of vertices x and y. I know there is a path between x and y in T. If this path does not contain the edge E, then I know that the same path still exists in the same graph where I have removed this particular edge. So that's great, right? So then I have shown that x and y are still connected in the new graph where I've removed this E. So now let's look at another case. For example, x is over here, and it is connected all the way through here, over this particular edge, all the way to, say, y over here. So this is case number 2. Well, are x and y still connected? Yes, they are, right? Because I have removed E from a cycle, so I can still go into the other direction of the cycle and connect back towards y. So what we see here is that x can go all the way to here, but it can still go over the cycle back to here and then to y. So we are still connected. So this shows that in both of the cases, for any pair of vertices, even after removal of E, the graph T minus this edge E is still connected. So let's write this out. So all vertices in G are still connected after removing E from T. So now we're done. So why was that again? We now constructed a smaller graph, smaller in the sense that it has one less edge, that is still connected and with the same vertices as G. But I assumed that T was already the smallest such graph, such subgraph, so we have a contradiction. So what does this mean? This means that our original assumption that we have over here cannot be true, because we started off with this assumption. Because of this, we could start to construct this, and then we could derive this whole argumentation. And in the end, we get a contradiction. So our original assumption is wrong. So actually, this is not possible. There does not exist a connected graph G that has no ST. So the theorem is true. Okay, so this is an important theorem. So now we can start talking about weighted minimum spanning trees. So let's use this picture over here and assign some weights to this graph. So for example, we have 1, 2, 2, 3, 3, 3, 1 over here, another 1, 1, 4, and 7. And let's construct a spanning tree. So let me give an example over here. Oh, actually, this is an example that we have right here in the thick lines in green. So what is the weight of this spanning tree that we have here? Well, we simply add the weights of all the edges. So we have 7, 3, that makes 10, 11, 14, another 2, 16, 17, 18, 19. So the weight of this particular spanning tree is 19. So now the problem is, and that's the rest of the lecture, how can we construct a minimum weight spanning tree? One that has the minimum weight possible. So do you see another example? So could I swap some edges around or something like that, such that I can get a less weight? So, for example, over here I have, for example, this node over here, right, is connected by an edge that has weight 3. But I could also have connected it to this particular one over here, which has only weight 1. If I do this, I actually improve the spanning tree construction. So I will get something that looks like let's see. That looks like this. And now we have replaced 3 by 1, so we get 17. So can we do anything less than this? That's maybe, and it's still a tree, right? Because there's no cycle. Here we have this part over here. If you want to have a connected subgraph, I always need the 7 in here. Well, it seems like you cannot really replace anything by something cheaper, like any edge in here seems to be pretty necessary. Of course, what I could do is I could create other minimum spanning trees. So actually it turns out that 17 is the minimum weight. For example, I could, instead of this edge, I could use this edge. That's another solution. Or instead of this edge, I can use this edge. So let's, so how do we construct such a minimum weight spanning tree? Can we somehow find an algorithm that creates this? And that's the big problem of today. So let me write out one spanning tree that I will use for the rest of this class. And maybe I will use a little bit different color. So let's use red over here. I hope this is visible. So we have red, this one, and this one, and this one, and this one, and this one. This is going to be the spanning tree that I'm going to look at. This is also weight 17. Oops. So let's first define what a minimum weight spanning tree is, just to be very precise. And then let's have an algorithm. Maybe you have already ideas how this could be done. It turns out actually that if you just start with a greedy approach, you just start to add sort of the edges of minimum weight that you can still add without creating any cycles, you will get an algorithm that is going to do the trick for you. So that's kind of surprising. So let's talk about the definition. So the minimum spanning tree of an edge-weighted graph is defined as a spanning tree of G such that it has the smallest possible sum of edge weights. So, well, the algorithm that I'm thinking about here is very straightforward. Actually, I use this blackboard because this algorithm will be the focus of the rest of the lecture. Okay, so what's the algorithm? We actually grow a subgraph step by step, so one edge at a time. Such that at each step we want to add the minimum weight edge that keeps the subgraph acyclic. So this is our algorithm. Let's have a look how this works in this particular graph over here. So suppose I would start off with, well, if I start with this algorithm, I take, say, any minimum weight edge. Say I take this particular one. So this could be my first edge that I choose. Then I may want to choose another minimum weight edge such that I do not create a cycle. Well, which one could I choose? I could choose this one. I could also choose this one. With this one, I could choose this part. With this one, I could choose that part. I could also choose this one. So let's choose this one, actually. That would be our second step in our second edge that we select in our algorithm. These are two disjoint edges, so there's definitely no graph. Well, maybe in our third step, I can choose one of these edges, which also has just weight 1, which is minimum weight. So this could be my third possibility. Then what's the fourth possibility? Well, I have to choose one of those, actually. I cannot choose this weight 1 edge. Why not? Because that would create a cycle. So I'm not allowed to choose this one anymore. So I choose one of these two. So for example, I choose this one over here. That's the fourth edge that I add to the whole picture. So notice that in the meantime, I have two disconnected components, right? One over here, which is this arc, and another arc over here. Okay, so which edge do I attach now in the algorithm? Well, I can still add this minimum weight edge over here of weight 2, because it does not create any cycle. So this would be the fifth one that I add to the whole picture. Well, now I can choose either one of those. So, for example, this would be my sixth step. And then finally, I can choose none of these, because those would create cycles. But I can choose this one. So this is going to be the seventh one that I add to the whole graph that I construct here and grow in this algorithm. It turns out that this algorithm actually creates for you a minimum spanning tree. And the proof is much more complex than what we have seen before. So that's what we're going to do right now. So when we think about this algorithm, then somehow I want to guarantee that at every single step, I will be able to grow into a minimum spanning tree. And that's the basic intuition that we have, and that's the lemma that we want to prove first. So, formalizing, we get the following we want to prove the following statement. So the lemma that will help us is let S be the set of edges that I have been selecting up to now in the algorithm. So let S consist, for example, of the first n edges and what we want to show is that we can still extend this set of edges into a minimum spanning tree. We can still grow within the algorithm into a minimum spanning tree. That's what we want to show. So we want to show that there exists a minimum spanning tree, T, that has the vertex set V and an edge set E. So this is a minimum spanning tree for the graph G, such that S is actually a subset of the edges in this minimum spanning tree. So this is a nice mathematical formulation that really precisely states that we can still keep on growing into a minimum spanning tree. So how would this lemma help us in proving the theorem that we want to show? Actually, where is the theorem? I did not write down the theorem so far. So let me put it over here. So the theorem that we want to show is that for any connected weighted graph G, the algorithm creates a minimum spanning tree. The algorithm produces a minimum spanning tree. So how can we prove this theorem? Suppose we know that this lemma is true, which we will prove later, then how do we know that this theorem holds? Actually, I'm wiping out this particular theorem over here. We will use this in a moment. So we know that every connected graph has a spanning tree. We already know that. But now we want to show that we can even construct a minimum spanning tree for a weighted graph. Okay, so how are we going ahead? The proof of the theorem is as follows. Well, suppose that the number of edges, the number of vertices, is actually equal to n. And if we want to show that we get to a minimum spanning tree, we want to first of all show that the algorithm is able to choose at least n-1 edges, right? Because a tree has n-1 edges. We have shown this before. So the algorithm should not get stuck. So let's first prove that. So suppose I have chosen less than n-1 edges. So suppose we have less than n-1 edges picked. Well, then what do we know? Well, there exists an edge in E minus S. So let's, let me first write it out. That can be added without creating a cycle. So why is this? I know that E is the edge set of my minimum spanning tree. I know that S is a part of, is a subset of all the edges. I know that the minimum spanning tree is a tree. It's a tree on n vertices. We know that a tree on n vertices has n-1 edges. I know that less than n minus 1 edges have been chosen so far. So that means that S has less than n minus 1 edges. E has exactly n minus 1 edges. So there's at least one edge that is contained, that is an element in E, but not in S. And for that particular edge, well, since it's part of this tree, together with S, which is also part of all the edges within the tree, well, we know that that edge, for that reason, will not create a cycle, right? Because otherwise, the original tree would have a cycle. Okay. So we know that the algorithm can always select an edge such that no cycle is created. And that means that we can keep on going in the algorithm until at least n minus 1 edges are selected. So what happens if we have n minus 1 edges? So once n minus 1 edges have been chosen, well, then S has exactly n minus 1 edges. E has exactly n minus 1 edges, because it's a tree. They are subsets of one another, so they must be equal to one another. So essentially, what we have here is that S exactly defines the minimum spanning tree that we are looking for. So the algorithm, at the very end, when it has chosen n minus 1 edges, produces a minimum spanning tree. So we know that S defines the edges of a minimum weight spanning tree. So if this lemma really holds true, then this theorem can be shown. So now let's have a look at this lemma, and we're going to use that picture over there to see how we can prove this. So this is a little bit tricky. And the way to go about this is actually to use induction. So let's see whether we can do this together. So the proof of the lemma is as follows. You want to use induction. On what do you think we are going to induct here? Well, we want to prove this particular lemma. We have this particular variable m, so that seems to be a good method to continue. So we use induction on m. And let's state the induction hypothesis. Well, it's exactly the same as in the lemma. So we say for all G and for all sets S that consist of the first m selected edges, there exists a minimum spanning tree of G such that S is a subset of E. So this is our induction hypothesis. And as always, we start with the base case. And the base case is going to be pretty straightforward in this particular case, at least. Well, we have to do a little bit of work for it. So let's see how that works. So the base case is m equals 0. So let's reread this statement where m is equal to 0. Well, if we have 0 selected edges, then S is the empty set. So I have to prove that for all G, there exists a minimum spanning tree such that the empty set is a subset of E. Well, the empty set is always a subset of E, right? So that's no problem. So what I need to prove is that for all G, there exists a minimum spanning tree of G. And this is where our previous theorem comes in, because we showed that for all graphs G, there exists a spanning tree, and if there exists a spanning tree, there also exists a minimum weight spanning tree. So that's the base case. So m equals 0 implies that S is equal to the empty set. So that means that S is definitely a subset for any set of edges of a minimum weight spanning tree. And now we're going to use our theorem to show that there also exists a minimum spanning tree. So this in itself is not yet sufficient, right? Do you see that? Yeah, I know that for if S is the empty set, then I know that this always holds, but the statement is a little bit bigger. For all G, I still need to prove that there exists a minimum spanning tree, and that's what our previous theorem told us. So we'll not write that part out. So we have the base case. Let's see. I think I will go and prove this over here. So let's look at the inductive step, and then hopefully we can play a little bit with this picture up here to get some insight. So how do we do this? Well, with an inductive step, we start as usual. Right? We assume that P of M holds. Now, how do we go ahead? So I want to prove P M plus 1, which is stated over here. So I want to consider the set S that consists of the first M plus 1 selected edges. So, well, essentially what I am interested in is what happens in the M plus 1th step. So let E denote the edge that I added in the M plus 1th step. And let S be the first M selected edges. And we know that we can apply P of M for S, right? Because we assume this is our inductive step. So we can apply something for S. We would like to show Pm plus 1. So we would like to show something for the union of those two. So let me repeat that. So let S denote the first M selected edges. So by our induction hypothesis, we can, well, let's apply it. We know that there exists a minimum spanning tree such that S is a subset of the edges. So let's just pick one such minimum spanning tree. So let T star be such a minimum spanning tree. It has edges E star and we know that S is actually a subset of E star. Okay. So let's look at the very first case. So what are the kind of cases that we are interested in? So let's think again. What do we need to prove? We need to prove Pm plus 1. So we need to prove something about the union of S and E. We want to show that there is a minimum spanning tree such that the edge set of this minimum spanning tree contains both S and also E. So what kind of cases can we handle here? Well, what would be a really good first case? The first case could be that E is actually already part of E star. Well, if that's true, then of course S together with E is also a subset of E star. And that means that we are done in this particular case. Why is this? Because this is an example of a minimum spanning tree that contains both S and E, so it contains the m+1 first selected edges, and so this is Pm+1. Now the next case is the difficult part. Okay, let's wipe out. Actually, we do not really need the proof of the theorem anymore. So let's take this off the blackboard. So the way to do this is to sort of see how we can use the tree T star and somehow transform it into another tree for this particular case, where we assume that E is not in E star. So let's have a look at that graph up there. Let me rewrite it a little bit, and let's look at what happens in the algorithm after 2 steps. So I will redraw the graph. So we have, say, these edges. This one, let me see. I want to use some different colors to make this as clear as possible. We have this one, we have this one, we have this one, and we also have this one actually, sorry. All right, so let's define the different edges. The straight ones form the set S. So after 2 steps over there, we have selected this edge first, and then this edge was the second edge that we selected in our algorithm. So these 2 together form the set S. So what is T star? T star could be, for example, the spanning tree that contains both these edges plus the dotted ones. So let's have a look here. This is indeed a tree, right? And if we look into this picture over here, you can see that the weight of this particular tree is 17. It's also a minimum weight spanning tree. Okay, what is G? G is the complete graph and contains not only these 2 types of edges, but also these sort of more orange-colored ones. So this is the situation that we are in. Now, in our algorithm, we want to choose this particular third edge. So this is going to be our E, this particular edge. And as you can see, E is not part of T star. It's not one of those 2 kinds of edges. It's actually one of the orange edges. So what can we do here? Well, the idea is that we want to recreate like a new tree in which we somehow exchange E, exchange one of the edges in T star with E, and still sort of maintaining the minimum spanning tree property. So how can we prove this? Okay. So the way to do this is to figure out what the algorithm teaches us about E, and also what the tree property tells us. So let's combine all our knowledge. So first of all, we know that the algorithm, from its definition, implies that S together with E actually has no cycle. That's how we select the m plus 1th edge. There's no, all the selected edges together should not contain a cycle. That's the definition of the algorithm. We know that T star is a tree, and this implies that if you look at the graph that has the edges, has the vertices V together with E star with edge E, then this must contain a cycle. Now, this property I will not prove right now, but it is pretty straightforward. It's a one-line proof actually in the book, so you can look it up. So it simply states that if you have a tree, if we add another edge, an edge that is not contained in E star, then we will create a cycle. So now we can combine these two statements together and conclude that, well, if S with E has no cycle, but E star with E has a cycle, and S is contained in E star, well, there's only one possibility, and that is that this cycle must have an edge E prime that is in E star minus S. Because if it would not have such an edge, then all the edges of the cycle must be located in S, but in S together with E, but S together with E has no cycle, so that's not possible. So this cycle must have an edge E prime that is outside S, but still in E star. So we can find one over here. E prime can be this particular edge. So E prime is in E star, but it is not already selected in S. Okay, so now we are going to do a trick. The idea is to swap E and E prime. So that's the main idea. So let's first write down what we know about the weight of E prime and E. So since the algorithm could have selected E or E prime. It did select E, right? But it could have also selected E prime, because E prime, does not create a cycle with S. That's what we have seen here. So this really implies, therefore, that the weight of E is at most the weight of E prime. So why is this? Because the algorithm always chooses the minimum weight. And it can choose between E or E prime, but it chose E, so the weight of E must be less than the weight of E prime. So that's what we know also. So now let's swap E and E prime in T, and then we're almost done with this proof, because that will be the tree of which we'll prove that it is a minimum spanning tree. Okay, so the key idea is to swap E and E prime in T. How do we do it? So, well, let T double star be equal to V with the edge set E double star, where E double star is really equal to, well, the original set E star, but we take out of this E prime. So this one is taken out of the minimum spanning tree, and we add E in here. Now we want to prove that this particular T double star is a minimum spanning tree that fits our lemma. So what do we know? We know that T double star is acyclic. And why is this? Well, we actually removed E prime from the only cycle So look up here also. The only cycle in E star together with E. So it's acyclic. T double star is also connected. And why is that? Well, since E prime is removed, but it was on a cycle, so it remains connected. And finally, we also know that T double star actually contains all the vertices in G. So all these three together will prove us that T double star is a spanning tree of G, because it's acyclic, connected, contains all the vertices. Is it a minimum weight spanning tree? Now we are really almost done, because let me write it out here. We know that the weight of T double star is at most the weight of T star. Why is this? Well, we showed just now that the weight of E is at most the weight of E prime, so we have exchanged E and E prime, so that means that the weight of T double star is at most that of the weight of T star. We also know that the T star is a minimum spanning tree. So if we combine these two together, then we know that the weight of T double star cannot get less than the minimum weight possibility. So it also has minimum weight. So T double star is a minimum spanning tree. So now we're done, because in this case we have constructed a T double star such that S together with E is a subset of E double star. And that means that we have shown that our induction step is true. We have shown that Pn plus 1 holds. So now we finally have figured out that the lemma is true. And now we can, and we showed already that how to use this lemma in our proof for this particular theorem. And so this is the end of this lecture, and tomorrow you will actually go again over this proof, because it's rather complex. And then hopefully you really get into all the different proof techniques. Okay, thank you.
following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So today we're going to talk about communication networks. Communication networks is a great application of graph theory. So what we're going to study is how do you route packets through networks. So you have the internet, which is a chaotic network. It's not organized. We are interested in highly structured networks. And you can find them, for example, in parallel computers where you want to route the data flow. You can find them in certain telephone switch networks, and so on. So we're going to talk about a few very special ones, binary trees, and then slowly we will figure out what all these performance measures really mean. This one has to do with latency. We have switches, their size, the number of them, congestion. And then we will slowly get down to Bennett's network, which is a really beautiful network with beautiful parameters, and we're going to prove those. So let's start off with the first one, the complete binary tree. And let me draw it for you. In this network, we will have a root. And let me just draw it first. We have vertices that represent here the switches. So these circles, let me explain it over here, actually represent a switch. And the idea is that these actually direct packets through the network. And these packets are fixed-sized packets of data, so like, I don't know, say 4,000 bytes or bits or whatever the network wants you to comply to. So these are fixed-size pieces of data. So what we want is we want to be able from every terminal, and the terminal I will denote by a square, from every terminal I want to be able to reach any other terminal. So what is a terminal? Terminal is like a computer or something like that. It's actually the source and the destination of data. So what we're looking for is how can we route, how we can find a network of switches that are connected through wires, fibers, or, yeah, that's the question.
The top of the that was getting cut off. No, that one.
Oh, sorry.
Oh, okay. Thank you.
So what we want is we want to route packets that come from any terminal to any other terminal. That is what our goal is, and we want to make sure that that is efficient. So the first one is this binary tree. And let's see how this may work. We may have switches that actually have inputs coming from terminals. And the switches may also output to terminals. These are here at the bottom. At this side, we have a similar structure. This is the root of the tree. We have another switch over here. We go down, we go up here, and once more, like this. And again, we have input coming in or an output coming out to their respective terminals. So what is happening here is that I would like to have an input, say input 0, wants to travel all the way over to, say, the output that is present over here. So let me label these. So we have the output 0, input 1, output 1, input 2, and output 2, input 3, and output 4. So, well, I can definitely reach every single output from any input. So that's great. So this looks like something that you are familiar with, right? It's like just a tree. We have, essentially, it's a directed tree, but I mean, it's a directed graph, but these edges go in both directions, right? So I have an edge that goes from here to here and back from here to here. So this is the kind of layout that you could try out first to see whether this type of network would lead to good performance. So let's have a look at the different parameters and see how well this behaves. So here we have a few parameters that we will be talking about. So first of all, let's talk about the latency in this particular network. So how are we going to measure this? Well, we're going to look at this graph and we're going to measure it by the number of wires that you need to go through from an input to an output. So let me write this down. So the latency is the time that is required for a packet to travel from an input to an output. And how are we going to measure this? Well, we're just going to measure this by the number of wires that we need to go through. So this you have seen before. We can measure this by the diameter of that particular graph. So here we will define it for a network. So the diameter of a network is going to be the length of the shortest path between the input and output that are furthest apart. So let's have a look at the graph above. So for example, we can clearly see that, for example, input and output, so say input 0 and output 1 are connected by just going up one step over here. But just going up from here to here, then this switch forwards the packet to this switch reroutes it, forwards it over here, and then it goes back to the output 1. So for example, this particular path only has 1, 2, 3, 4 edges. And what we're interested in is sort of the worst case time that it requires to go from an input to an output. So that means that we are interested in the diameter. And the diameter is, in this case, well, the shortest path that you can find from an input to an output that are furthest apart. So what are those who are furthest apart? Well, of course you would like to go through here, right? So if I connect the input 0 to, say, output 4, I will need to go all the way up through the root down to the output. And how many edges do we see here? 1, 2, 3, 4, 5, 6. So in this example, we have a diameter that is equal to 6. And in general, if we are looking at n times n network, so what does that mean? N is the number of inputs, and n is also the number of outputs. So in this case, we have a 4 times, oh, this is actually 3 over here. We have 4 inputs and 4 outputs. So this particular example depicted on the board is a 4 times 4 network. So if you generalize this for any size binary tree, say an n times n network, then how many, what's the diameter of this, of such a general network? Well, if we have n inputs and n outputs, well, we have to go all the way up towards the root and all the way down. So we actually count the length of a leaf to the root here twice. So in general, we have a diameter that looks like this. It's 2 times 1 plus the logarithm of n. So in this lecture, we will have n is going to be a power of 2, just to make calculations simple. And the logarithm is always to the base 2. So this is the diameter of a general binary tree. And well, what are the other parameters? So that does not look too bad. I mean, it's logarithmic in n, so that sounds pretty good. What about the switch sizes? Well, how do I measure those? It's like the number of inputs that get into it and the number of outputs that get out. So in this case, I will have 2 inputs that go into this switch, and there are 2 outputs coming out. So this is what we call a 2 times 2 switch. So this would be a 2 times 2 switch. But if you look at this one, for example, we see 1, 2, 3 outgoing edges and 3 ingoing edges. So this is actually a 3 times 3 switch. And in a general binary tree, we will see that all these intermediate nodes over here, they're all 3 times 3 switches. So the most, approximately half of the switches are actually 3 times 3 switches. So that's a switch size. Now you may say, well, why don't I use like a larger sized switch? That would help me a lot, right? If I could use, say, a 4 times 4 switch, then I would be able to have more inputs coming in, more outputs coming out, and I can actually maybe use a ternary tree rather than a binary tree. In a binary tree, every node at a level has like 2 children, right? But we could design a tree that has at every level 3 children. So then we can use 4 times 4 switches. If we do that, then the path from the leaf up to the root is getting shorter and the diameter gets smaller. So if I increase sort of the switch size, so rather than 3 times 3, we look at 4 times 4 or 5 times 5, 6 times 6, and so on, then the diameter will actually reduce. So what about having a monster switch? Like I have just one switch, and I have my input 0 all the way up to input n minus 1. And then I have my outputs on the other side. Well, of course, the switch size is n times n, but the diameter is nothing, right? You can immediately go from, the diameter is reduced to 1. You can immediately go from an input to an output through the switch. But this, of course, conceals the problem. So what we're interested in is, well, we're actually really interested in how to solve the problem of routing all these inputs to these outputs using smaller, smaller switches of size 3 times 3 or 2 times 2. What we're really interested in is, what is the internal structure in this monster switch? I sort of have concealed the problem by just saying, oh, I got a big switch. But, you know, what we want to solve today is, how do we do the routing in this case within the monster switch? So we want to use just small switch sizes and build up a network using these smaller ones, like 3 times 3 switches or 2 times 2 switches. That brings us to yet another parameter, because we would like to count the number of smaller switches that we use, and that relates to the cost of the network. the amount of hardware that you need to put into it. So in this example, we have the switch count. Well, it's pretty simple, right? It's 1, 2, 3, 4, 5, 6, 7. We have 7 switches. And in general, if we have n inputs, so 1, 2, 3, 4 inputs, then the number of switches that we use in the binary tree is 2 times the number of inputs minus 1. So let's write that down. So over here we would have 2 times n minus 1, which is the number of switches that you actually use. So how can you see that actually? So in general we have 1 plus 2 plus 4 plus 8 and so on plus n. N is a power of 2 according to our assumptions. And if you add them all up, I think well, you can check for yourself that this is actually equal to 2 times n minus 1. Okay, so now we have the switches. So far this looks pretty good actually. We use small switch sizes. The number of switches is linear in n. Diameter is logarithmic in n, so that sounds good. So what about congestion? Do you have any idea what's the problem with this graph? What is the big problem here? What can happen in a very, sort of a worst case scenario where the packets get routed from the inputs to the outputs? If they need to go to certain locations, then they may have to travel through the route. So you get congestion over here. We don't like that. So this route is actually then overloaded. Actually, you can already see that if, say, this particular switch, if this switch fails, then actually we will have 2 disjoint trees that cannot even communicate to one another. So this brings us to the idea of congestion. And in order to define it better, you will need a few definitions. So to start, we will define a permutation. And we will use this to stipulate the requirements that we want on how inputs and outputs are related to one another, which input needs to communicate to which output. So permutation is a function pi from the set 0 to n minus 1 to the same set. And it is such that no two numbers are mapped to more than once. So no two numbers are mapped to the same value. So what we really want, to put it in mathematics, right? We want that pi of I is only equal to pi of j. Well, if and only if I is equal to j. So let's have an example to plug into that picture over there. So a first example could be pi of I equals, say, n minus 1 minus I. This is a proper permutation. No two numbers map to the same value. Another one could be the identity permutation, like you map I to the same I. So that's another example. Now, how do we use permutations to go towards the idea of congestion? So permutation can be used to formulate the permutation routing problem. And the permutation routing problem is defined like this. It's defined as follows. What we want is that for each I, we want to direct the packet at input I to output pi of I. So you want to do that for all I. So let's have a look at this particular example where we look at the identity permutation. So if you do that, we can easily route these, right? So I want to send a packet from input 0 to output 0. So I can simply go into this direction. I just go towards this switch and it gets routed back to this one. I can go like this, and this one can go like this, and this one goes like that. Now if you look at the other permutation, the picture looks very different. Now we want to route input 0 to output 3. In order to do this, I will actually need to go all the way through here and then all the way down to this particular output. And now the picture gets into a big mess because for input 1, we have to go to output 2. So for input 1, well, we go all the way like this. We again go through the root, and then we go down to this particular output. And as you can see, for input 2, we need to connect to output 1. So again, we go all the way up, and we go all the way down. And for this one, we will again go all the way up and all the way down to input 0. So now you can see that this particular switch over here has to serve packets from all the inputs. All the 4 packets have to travel through this particular node here. So this leads us to the following definition of congestion. So the congestion before we continue, let me first define a path. So for each I, we direct a packet at input I to output pi of I. And the path that corresponds to this route is actually denoted by as follows. So the path taken is denoted by P I pi I. So now we can define the congestion of a set of such paths. So the congestion of the path corresponding to P0 to P pi 0, and so on, and we go all the way up to the n-1th input that needs to be mapped to pi of n-1. So the congestion is now defined as the number to the largest number of paths that pass through a single switch. So in our example, we saw that in the case of the blue arrows here, which for the identity permutation, well, this switch only needs to transmit 1 packet, and all those actually 0 packets. So actually the congestion here is equal to 1. And for this particular permutation, well, we had to direct all the packets through the root, and that's the most accessed switch, and that switch has congestion 4, right? So the congestion over here is equal to 4. Now this does not look so good, because for a binary tree, we always have this vulnerable root that is right here in the center connecting the left side to the right side. So I can always find a permutation, actually this permutation over here, that leads to this worst case congestion. So what we're interested in is the maximum congestion, which is sort of the worst case scenario, and we'll define it as follows. The maximum congestion is actually equal to the maximum over all permutations pi. So this is kind of the worst case routing problem that I can imagine and that may occur in practice. So in the worst case, how can I solve it the best? So I want to find the minimum of the congestion. I want to find the minimum congestion of paths over here. And the minimum is over these types of paths. So actually, this is our solution to this routing problem. We want to find the best kind of solution for this worst case scenario. So the minimum over all solutions for these paths. So, well, for this particular tree structure, this permutation is really the worst case scenario that you can have, because every packet needs to be routed through the center over here. And it means that our maximum congestion for an arbitrary tree is actually equal to n. So now that looks really bad, actually. So we don't like this at all. So let's find out whether we can do a little bit better. And we're going to look at the two-dimensional array and see what that would lead up to. And its structure is as follows. We essentially have inputs on the left, and the outputs are on the bottom, and they are in a grid structure. So we have input 0, input 1, input 2, input 3. They all connect to their terminals. We have switches, 4 of those, and they are all connected in this grid. And at the very bottom, we will have the outputs, the output terminals. So this is output 0, and here we will have output 1, output 2, and output 3. So I notice that my circles start to resemble my squares, but these are all the switches right here in the center. So how does this work? Well, do we have a better parameter? So let's look at it together. So we need to first of all figure out what the diameter is. So what's the diameter of this particular network? So what's the shortest path between the furthest input and output? So, well, if you look at that, we can see that if I go all the way from here and I go all the way down to this corner, that looks like the largest path, and I need to cross all these wires. And in general, for any n, we will have that the diameter is 2 times n. Now, what about the switch size? It looks a little bit smaller, right? Because over here we had 3 inputs coming in and 3 outputs coming out. But over here, we see that every single switch has only 2 inputs and 2 outputs. So that makes the size 2 times 2. Now the number of switches is pretty bad, right? Because we have n square switches. So that's really horrible. That's a lot. We would like to do much better. And what about the congestion? Do you have any idea what the congestion could be in this particular case? We will prove a theorem on that. So is there a way to map, for any permutation, is there a way to map the inputs, to route the inputs to the outputs in such a way that the switches get almost not congested? So in the binary tree, we had a congestion of n, which is linear in the switches. But over here, we can do much better. We will show that the congestion of an n-input array is actually equal to 2. So that's great. So I'll prove it in a moment, but that looks really fantastic. And so it's way better than the binary tree. Now this is really not so good, and this is also much larger, but still, we will start to think next, after we show this particular property, how to combine these two and see how we can come up with another network that's maybe that's able to combine in some ways these two properties. And maybe we can find a good solution that way. It turns out we will not immediately be able to do that, and we will need to make another step and come to the last network that really has good parameters. So what about the theorem? So if we prove this, well, how do we start? You just start with any permutation. If I want to prove something about congestion, it's defined as the maximum over all permutations. Well, let's take one of them and see what we can prove. So let's just define the paths for this permutation as follows. So what we really want to do is we take any permutation and we want to find a really good solution for the routing. If that gives us a very low congestion, we're very happy. So the way to do this is, well, maybe you have an idea already. So how would I route this? So I want to connect an input I, say 1, to output 2, for example. How can I do this? Any suggestions? So of course I could go any path, but somehow I want to have some uniform structure that hopefully helps me to prove that the congestion in every switch is very small. So how could I think about this? If I make sure that, say, a packet that goes from 1 to output 2 is only going to be participating in the wires of the ith row and the pith column, then I know that every wire will only get traveled over twice by a packet. It could either be a packet that goes into this direction, or so a switch will be accessed at most twice. A switch can either receive a packet from this direction or receive a packet from the upper part. So that will be a really good idea. So let's define that. So we say that in our solution, we will design it such that the path from input I is actually going to be rightward to column pi I, and then downward to the output. So downward to output pi I. So this is a really good solution to the routing problem, because now we can continue our proof as follows. We just say, well, if you look at the switch in row I and column pi I, well, this one actually transmits at most 2 packets. because a packet can only come from the left, or it can go from the top. So either one of the two, at most those two packets will go through the switch. So this shows that we have a congestion of at most 2 for any permutation. And in order to prove equality, because that's really what the theorem says, we also have to show that there exists a permutation that achieves a congestion of 2. And that is pretty straightforward. We can, for example, use a specific permutation that maps 0 to 0 and maps n-1 to n-1. Well, for this particular permutation, when we look at the picture over here, we see that input 0 needs to go to output 0. We also see that this lowest input 3, needs to travel all the way up to here. But it's clear that the packet that needs to go over here needs to travel through that switch in the lower left bottom corner. And the input 3 also needs to travel through that. So here we clearly see that we have a congestion of 2. So now the proof is complete because we have shown this upper bound. So for any permutation, the congestion is at most 2. And we see that this specific permutation achieves this congestion. So this is the end of this proof. Okay, so that's great. So now what we like to do is we like to combine these two networks and see whether we can learn from both. So now we'll be taking out a lot of chalk over here. So the idea is to construct a butterfly network, and I will draw it in such a way that you can see the recursive structure. And the idea is to do the following thing. So let me see how I can do this the best. So I will just do the top line first, and I have the spacing. So we have input 0, a terminal. We have a switch. We have a switch. We have a switch and another one. And here we have the output 0. So the whole idea is that I'm going to combine every two outputs by using a small butterfly structure. So we have 2, output 3, output 4. Actually, I need a little bit more space. Do it once more. Output 1, 2, 3, 4, 5, 6, and the last one, 7. Okay, this is going to be pretty tight on the board. So what's happening is this. So these are all connected, of course, to switches. The switches output those. And the idea is that we create the following structure. This switch can either forward it over here or can cross it over to this particular line. And this switch can either forward it or cross it over to this line. So this is a very small butterfly structure where we have 2 inputs and 2 outputs. And we will repeat this process, and we'll do the same on each of these other levels. So we forward those or we cross them. Like this. And now that we have constructed all these smaller butterfly structures, we can start to combine 2 butterfly structures together in the bigger one. So here we had two outputs that we combined in a butterfly structure. Now we use two butterfly structures that we put into a bigger version. So how do we do this? Well, we have that the upper half over here can either forward those packets or cross them over to the bottom part butterfly structure. So for these, we can either forward them straight on, or we can go to the top butterfly. So you see that these two inputs, these two switches, either can forward packets to this sub-butterfly network or to the top butterfly network. Now we'll continue this process. And for these we'll do the same. So we can either go straight or we go down. And over here we can go straight or we can go to the top butterfly network. Well, now we have the final part where we combine essentially these two butterfly networks. We have two butterfly networks created here now, composed again of smaller ones. And now these two are being composed to this bigger butterfly network. Again, we take these four switches. They can route their packets forward to the top butterfly subnetwork or to the bottom one. So they can either go straight ahead, or this one can connect to the first over here, this one to the second, to the third, and this to the fourth. And in the same style, these can forward them straight like this, and then go up. Like this. And these are all connected because in this example we just have an 8x8 network, butterfly network. We have inputs 0 to 7. Okay. So this is the butterfly network. In a way, what you can see here, you can see sort of the two-dimensional structure, like we have rows and columns. At the same time, we can also see this binary sort of tree feeling we get from it, which is that a switch can forward its packets to either, say, the top butterfly or the bottom butterfly. So there's a split in two. The same for this one, right? This one goes either to this butterfly network or it goes to this butterfly network. So you have this tree structure sort of embedded in this two-dimensional structure. So what are the properties of this one? So let me first define like in more formal mathematics, how the switches route their packets. So how their connections are. So in order to do that, we're going to label each switch. And the idea is that we're going to label it by its row and by its column. So we will have the columns are numbered by level 0, level 1, level 2, level 3. Yes. And the rows are these integers, but we're going to represent them by binary numbers. So 0 would be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and then we got 1, 1, 0, and 1, 1, 1. So, for example, this particular switch would be labeled by these 3 bits, 0, 0, 1, and the integer number 1. This one would be 0, 1, 1, and its column is indexed by integer 2. Okay, so a switch is uniquely identified by its row and column. We will have b1 up to b logarithm of n, which are the number of bits to represent the row indices. And we finally have an integer L, and this we will call the level. So this particular switch either directs or routes a packet to the switch that is indexed by B1 up to, and then we get BL plus 1, and we take its complement. So instead of, if BL plus 1 would be 1, we would have a 0 here. If it would be a 0, we will have a 1 over here. But we repeat all the other bits, and we get B log n. And it routes its packet to the next level, so we will have L plus 1. Another possibility is, because there are two outgoing edges, is if we have just B1, and we just copy BL plus 1, essentially. We route the packet straight forward. We don't do anything special. We get B log n over here, and then to the next level. So for example, let's see whether we can see how this works. So for example, take this particular switch. We have 0, 1, 0. So it can either go straight on to the next level. It would go to 0, 1, 0, but then instead of level 1, we have level 2, which is the right edge over there. The other one is if this one goes up, well, we will need to switch the first bit over here, 1. We swap it into 0, and then we go to the 3 zeros over here, and we go to the next level, and that would be this particular rule. So what we can do here is to, when we see this, we can start to figure out how we can direct inputs to outputs. Okay, so let's do this. So suppose I want to route a packet from a certain input, one of these, all the way to one of the outputs over here. So the way to do this is as follows. We can just start, for example, I want to go from switch x1 up to x log n, comma 0. So I start completely at the left over here, and I want to go somewhere of my choice to the right. So I want to somehow move all the way to some other row, y1, indexed by the bit pattern y1 up to y log n, but now at the very last level, which is log n. Well, how do I do it? Well, this switch, I can use that rule up there and simply change x1 to y1. I can either leave x1 as it is, if it's the same as y1, or I can swap it to its complement, if that's the value of y1. So what I can do is I can just simply route it to y1, and then I leave all the other bits the same, which are x2, x3, all the way up to x log n. And we will have reached the first level. Now this one can go to, well, now I'm going to swap the second bit into the bit of my choice. So I leave all the other bits the same, y1 the same, x3, all the others the same. I just swap x2 into y2. So we leave all those equal. And we go to the second level. And then we go all the way to the final level, and we one by one swap all these bits. So let's have an example. suppose I want to connect, say, this one to, for example, well, let's say this particular output. So what's the binary for this one? This is actually 1, 0, 1. So if the first bit is different, I need to cross, and otherwise I need to pass straight on. So let's do this. So over here, I'm in 0, 1, 1. I need to go to 1, 0, 1. So I need to change the 0 into a 1. So I need to go down. I need to cross. Now, if I look at the second bit, I also need to change it into a 0. So again, I need to cross, which is over here. Now the third bit is equal to 1. And it's the same. So now I can go straight ahead. I do not cross. And I end up at this output. So what did I do? For every bit that is different, I cross. And for the bits that are the same, I go straight ahead. So this is how I can route packets from one input to another output. Okay. So let's look at the parameters. First of all, if we look at the diameter, well, it turns out that that's approximately equal to the number of levels, which is the logarithm of n. And to be precise, it's actually equal to 2 plus the logarithm of n. So that's great. That's a good scaling. Again, it's back to the logarithm of n. So we have the best of these two parameters. The switches that we see have 2 inputs and 2 outputs. So we again have a 2 times 2 switch. The number of switches is the number of rows times the number of columns. The number of columns is the logarithm of n, and the number of rows is equal to n. And to make it a little bit precise, it's 1 plus the logarithm of n. So that's somewhere in between those two, but if you're thinking about it, it's much better than n squared. It's almost linear, except for a logarithmic factor. For the congestion, and we're not going to talk about it here, but you have a problem set assignment that will ask you to solve this, is that actually the congestion is the square root of n, or it's equal to the square root of n over 2, depending on whether n is an even power or n is an odd power. Now, we're not going to prove that here, because we want to step forward to this particular network. It's very exciting. And you will prove this in your problem set. So this one is somewhere in between these two extremes. Now, it would be really fantastic if we can somehow transform this network with a trick to, again, have a really great congestion of just a constant, like 2 or 3 or whatever, or maybe even 1. So for this particular network, in the 1960s, a Bell Labs researcher had the great idea to use a butterfly network and attach to it, again, a butterfly network, back-to-back, sort of. So what was his idea? His idea was to do the following. So the butterfly network, as we have it right now, is this particular part over here. And the idea is to now to start up mixing all those outputs that we got here together again using a similar rule. So what do? We are going to essentially repeat this particular structure on this side. Okay, so how do we do it? Well, we go either straight forward, or we start to mix them again. So it's like this output, this particular switch can either go straight ahead or can cross to the lower part over here. It goes over here, and this one goes over here. So as you can see, we have repeated this part. Is exactly the same as this structure over here. And we'll do the same for this part. So we can either cross or we can go straight ahead. We also have, of course, that these switches can go straight ahead or can cross to the top. I forgot about that. So we have this, as well. So as you can see, this particular structure repeats itself again, and we slowly start to build up and mixing all the outputs again, or the possibility at least to route them to any other row. So how do we do this? Well, we continue this particular structure now over here. So all these can either go straight ahead, that's a possibility, or they can go all down. So this switch can either go straight ahead or can go to the lower half. And for these we have a similar structure. We can either go straight ahead or such a switch can cross over to the top over here. Okay. So that's this. So this is Bayes' network. And then over here, of course, we have the outputs 0, 1, and all the way down to 7. Okay. So as you can see over here, this structure again has a recursive nature to it. You can see that this big Bayes network over here consists of two smaller ones that are right here in the middle. This one that goes all the way up to here. So maybe I should put a color boundary around it. Let me check how I want to do this. Right, so this particular part is again a Bayes network, and the top part in the same picture, the top subnetwork, is also a Bayes network, this part. And if you look within those, we again see a top part and a bottom part. And over here we see a top part and also a bottom part. So you see this recursive nature again reappearing. It turns out that with this trick we can completely eliminate congestion and we can get it to only 1, which is really surprising, and that's what we're going to prove here. So this is a great invention at the time. It's really, really beautiful. So let me put in the other parameters. So they stay approximately the same up to that the diameter is about twice as large because we added another sort of whole butterfly structure to it. The switches sizes stay the same. We again have about 2 times more switches. So they sort of stay about the same up to a linear factor, like a constant factor. And the congestion, however, completely dropped down to 1. So that's what we're going to prove now. And in order to get some intuition, well, let me first write down the theorem. Actually, let me put this over here. So in order to get some insight into this, we are going to, we are going to use this recursive nature. So we're going to use induction, and we're going to say, I can really, for any permutation, I can find a really good routing for, say, this red subnetwork and for this blue subnetwork. So I know that. So what I need to do is if I have my bigger Bennis network, like this one, I would need to somehow map these inputs. I need to route them to either the top and the bottom subnetwork, one of the two, in such a way that there will be absolutely no congestion, because we want to keep this one. So a switch should only see one packet coming in. So that means, for example, and we'll come back to that for example, for this switch, it should not receive a packet from both this input and from this input. So the intuition that we are going to create is we're going to create like, we're going to list our constraints, the constraints that we need to satisfy, like the 0 and the 4th input should not both be mapped to this top subnetwork, and so on. So we will get into that, and then we will gain a lot of intuition on how to solve this. Okay, so what's the theorem? So the theorem is that the congestion of the n input Bennis network is actually equal to 1. And we will prove this for n equal to a power of 2. We have assumed that at the start with all the other networks as well. And in this case, we will use induction on A. So that's the method that we will do, because that's also the recursive structure of the Bennis network itself. So we will use induction on A, and we're going to define the induction hypothesis simply as the theorem is true for A. Okay. Now let us do the base case. We always start with the base case, and that should be pretty easy because this is the most basic Bennis network. So n equals 2 to the power 1. We essentially have two inputs, an input 0 and an input 1. They are connected to these switches over here that can either forward them or can cross them over, and then they go directly to the output. Notice that in this case we just have the most elementary butterfly network. It's the same. So we have output 0 and output 1. So this corresponds in this picture to these little small things over here. This one and this one and this one over here and the fourth one over here. So now let's take any permutation. We want to show that we can route it in such a way that there's only a congestion of 1. So let's do this. So there are essentially only two permutations. Either 0 is mapped to 0 and 1 is mapped to 1, or 0 is mapped to 1 and 1 is mapped to 0. So in both cases, we can just route them through their own switches. So we have that either pi of 0 equals 0 and pi of 1 equals 1, in which case we just direct them straight through. There we go, straight through, and every switch only sees a packet once. So for this particular permutation, we have a congestion of 1. Now the other permutation that we can have is if 0 is mapped to 1 and if 1 is mapped to 0. Well, in that case, we just route this cross over to the bottom row, and here we go from this switch to the top row. Again, every switch only sees a packet once. So in this case, in the base case, we are done, we are happy, we have shown that the congestion is equal to 1. So now we get to the harder part, because for the inductive step, we are going to assume, of course, that it holds true for a smaller Bayes network. So we assume that PA is true. And, well, let's try to gain some insight here. So we know that within each, from our induction hypothesis, within each subnetwork, we can achieve, we can solve any routing problem with congestion 1. And for this subnetwork, the same. That's our induction hypothesis. So how do we go ahead? We need to somehow map these inputs according to the permutation of our choice. So that could be, for example, input 0 goes to output 5, or input 1 goes to output 2, etc. So somehow we need to choose where we are going to map this particular input to. So the packet that goes, packet 0 that comes from this input, should either go to the red network or it should go to the blue network. And for each of these inputs we can make such a choice. But we have to be very smart about it, because we need to avoid any congestion. So the intuition is that we're going to set up a constraint graph. A graph that represents all the constraints that we need to satisfy in order to achieve congestion of 1. So let's do an example such that we can figure out what's going on. Actually, let me put that over here. So just take an example permutation, and we'll go through this example and then see how the proof works. So let's, as an example, have pi of 0 maps to 1, pi of 1 maps to 5, pi of 2 goes to 4, input 3 goes to 7, 4 maps to 3, 5 to 6, 6 to 0, and 7 to 2. So this is just an arbitrary permutation. And okay, so what do we see? We want to make sure that, for example, this switch is only seeing one packet. So it cannot see a packet both coming from input 0 as well as from input 4. I cannot see that. I do not want that to happen. Similarly, for this one, I do not want to see a packet coming from 1 or one from 5. So let me define a constraint graph that sort of represents this. So the constraint graph that we are interested in is defined as follows. If two packets must pass through different networks, subnetworks, so in our case the red and the blue subnetwork, then we'll actually have an edge between those two. So then there is an edge between them. So for this example, we're going to set up this constraint graph. And so I was just talking about this particular switch. It cannot see one coming from 4 and a packet from 0. So what we do, we have an edge between 0 and 4. In the same way, we have an edge from 1 to 5. Why? Because a packet that comes from input 1 and a packet that comes from input 5 cannot both be routed through this switch, because then the switch would see 2 packets, and then the congestion would not be 1 but 2, right? So 1 and 5 also have an edge in between. And in the same way, we have 2 and 6 and 7 and 3. So 2 and 6 are is this constraint, like 2 and 6 over here, and 3 and 7 is the other constraint. So if I have those constraints in place, well, then I know that the routing that goes from level 0 to level 1 will not violate my congestion of 1. So that's great. Then I hope to be able to use the induction hypothesis, and I get a proper routing within the red subnetwork and one within the blue network. And then I need to map all these to these outputs. So I also have constraints on these outputs because, well, for example, take this particular switch. It should not see a packet coming from this particular one and one from this one. So how do I code that up? So, okay, so let me first write out what we did here, and then we'll do the same for the last level over there. So, oh no, that's not really necessary. Okay, yeah, so at the output side over here, we have similar constraints as we did over here. And in this particular example, just as an example, suppose we look at the packet that is destined for output 0. Well, what is this packet? Well, I know that pi of 6 is equal to 0, according to my example. So packet 6 is destined for this particular output 0 over here, and goes through this particular switch. So this packet, and also the packet for output 4, which is, if you look at the mapping, pi of 2 is equal to 4, so that's packet number 2. Well, both of these packets cannot pass through the same subnetwork. Cannot pass through the same subnetwork. So why is this? So let's look at this particular example. So output 0, well, comes from packet 6, somewhere over there. Now suppose packet 6 was routed through the red network, and at the same moment also output 4, the packet that is destined for output 4, which is packet number 2. Suppose packet 2 was also going through the red network. Well, then I notice that both of these packets must arrive at this particular switch in order for one to be routed to output 0 and the other one to be routed to output 4. So in order to avoid congestion in this particular switch over here, we need to have a constraint. The constraint says that the packet for packets 2 and 6, that those two cannot go through the same subnetwork. So we essentially have another edge over here. We already had the constraint, but it's just the same edge. So let's look at the other constraints that we have. Well, for example, well, let's look at a different example. So, for example, if I look at this switch, well, it can, if a packet goes through here that needs to end up at 1 and a packet that goes to 5, if those two packets are routed through the same red subnetwork, they have to end up here in order to go to both here and to there. So I have congestion of 2. So what are those packets? Well, what does pi map to? To 1 and 5. Let's look over here. We see that pi 0 is equal to 1, and pi 1 is equal to 5. So packet 0 and 1 are actually mapped to output 1 and 5, and they should not go both through the same subnetwork. Okay, so we have another edge over here. And now we can continue this. And we have 5 and 7. So just have a look over there. Say 5 and 7, they map to the outputs 2 and 6. Again, we have 2 and 6. If they are both mapped to the same network, this one, for example, then I will have a problem. Okay, so the other edge is over here. Okay, so what did we do here? We started to write out the constraints on this side, and we wrote out the constraints on this side. So I only looked at the red subnetwork. That's what I realize now. I could also have looked at the blue network. So let's do that also, just to make the picture complete. So for example, let's look at this particular example. The packets 6 and 2 should not both be routed through the blue network, because then they would both have to go through this switch. One going up to output 0, and one going to the left, to the right, to output 4. So in order to avoid congestion at all costs, we have this constraint graph. So now we come to the key insight. And the key insight is to use a 2 coloring of this graph. So the key insight is a 2 coloring of the constraint graph, which will lead to a best solution for the routing problem. Okay, so let's do this. So we will color this one blue. As you can see, this is an even cycle. Blue, red, blue, red, blue, and red. We'll make this one blue and this one red. Well, it turns out that we can now start our routing process. So for example, actually I will draw a new graph to make that really clear. So I have my blue and my red chalk over here to demonstrate what I mean. So what do? I have 0, 1, 2, 3, 4, 5, 6, and 7. I have the switches that correspond to those. Well, if it's colored red, so 0 over here is colored red, I will direct it to the red subnetwork. So where is this red subnetwork? It's really contained over here. And the blue one, so this is the red one. And the blue one is right here. And over here we have the outputs, ranging from 0, 1, 2, all the way to 7. Okay, so input 0 is colored red. We go straight ahead. We want to go to the red network. Input 1 is colored blue. It goes, therefore, to the blue network. So this is the only way how to do it. Input 2 is colored red. Go straight ahead. Input 3 is also colored red. Go straight ahead. Input 4 is colored blue. Goes to the blue network. Input 5 goes up to the red network. Input 6 goes straight ahead to the blue network, is colored blue, Input 7 is also colored blue. Okay, let's look at the outputs. So, for example, well, let's have a look at output 0. So output 0, which packet is mapped to output 0? It's packet number 6. So 6 was mapped into the blue network, and then it needs to be mapped to output 0. So there's only one edge that goes from the blue network to output 0, which is this particular one. And then somehow this one needs to be mapped to this one over here. Now we can continue like this. Output 1 should receive a packet from, let's look at the permutation, from 5. So, output 1, pi of 0 is equal to 1. So packet 0 needs to go to this particular output. Now packet 0 is in the red network, so there's only one edge that goes from the red network to this output. So we need to have a connection over here. Now we can continue this and note and demonstrate, and you can test it for yourself too, that output 4 needs to receive a packet from the red network. Actually, it should be this particular one, which happens to be packet number 2. And then we have this one, right. So let me just finish it. We have this, and we have these two, and we have this one, we have this one, and we have this one. This one goes straight ahead. This one goes all the way up, and this one goes all the way up. So what do we see? We see that packets over here, that these switches only see a packet once, and these ones as well, these one also, and these ones also. So we have directed the packets, routed the packets to the red and the blue sub-networks in such a way that the congestion at the last level and at the first level is still equal to 1. Now we use our induction hypothesis, and we conclude that we can map the route, that we can have a routing from packets from here to here, such that the congestion within the subnetworks is only 1. So within the blue as well as in the red. So this is the insight into how this works. And I notice I'm running out of time, so the formal proof we will have to postpone till recitation. But that's actually really a very simple thing to do that right now, to just keep this key inside, and then you can easily prove the theorem. So, but this is the real insight. Thank you.